Working, yeah.
I want to get it to the front that.
Posters, posters.
Oh, yeah. This is a lot. Like the criteria, LLM space. What about? It's like zero. Yeah. Throwing off robots. Building the pad, like, video thing for other things. Track this phenomenon, virgin misalignment. No, I fine tuned elements. What is observed. At the same time, just just this unrelated. I guess that's what we like generalize it. Yeah, that's what it is. Yeah, that's what we want.
I'm gonna try and make sure that this is.
Yes, I'm going to.
We'll see you soon. What is, it says it's still pending?
There's this.
Oh, nice. Oh, so it's working.
Can you check on your laptop?
Yeah, let
Oh,
me.
you got a better use of Zoom, huh?
So the Zoom feeds to YouTube Livestream.
Yeah.
Yeah.
That's.
Let me try sharing my screen with Matthew's slides. You sent us an email, right?
Chris, yeah, so UN in Israeli.
Here it is.
That one.
Yes. Yeah, we can try setting up Matthew's slides. Hopefully it will.
Should work, right?
It should just work, yeah.
I'm so hungry.
Same.
So far, it's been going all right.
Yeah, I think it's been decently smooth.
Okay, so now what, let's say I have to share my screen now,
Yeah.
right? So let's go like, let's move those slides. Or no. Let's just share,
Yeah. Should share desktops too.
do like this, because
Yeah, it will, yeah, that works. If you just share desktop too. Cool.
how's that?
Fine, just make sure. All right. Yeah, looks pretty clean.
Yeah, okay,
But
let's,
how come that's not coming through?
I think it's, there's some lag.
Yeah.
Thanks, Matthew. This is only, yeah, see. There's just lag. Yeah, see, and now it's you flipping through it. Okay, I'm gonna add this link to the website.
where's the dongle?
1 sec, 1 sec. Joey, you're gonna have to check again.
Okay.
Data is too boring. Instead, we collect a large egocentric human task-oriented dataset. Here, task-oriented means the human data has clear start, end, and focus on specific tasks, just like robot data. We
What dongle?
advocate human-centric representation, which represents actions.
That doesn't work.
And
They said it doesn't work.
it's an embodied nothing representation that applies to any.
I don't see a USB on this. It's a Mac. What are you trying to connect? Is that audio?
Yes,
Oh.
this is the main audio cable.
That must be, that needs a dongle. That needs a USB-C dongle, it looks like.
Ah, there is. And that's the
That's-
remote
that's the
living,
big one. Maybe one of the organizers has a USB-C dongle.
I gotta find it.
They want to, you have a dongle for that USB-C?
I do, but it didn't work earlier,
Oh,
so
fun.
we have a backup.
This is for projecting the audio for that video you got.
But we'll make
Worst case,
it,
you could have the speakers run and then just the microphone pointing at the speaker.
but then you get the feedback.
You do?
Yeah, you'll get the
brutal?
feedback from.
Yeah, it's true. Yeah, I didn't realize that.
Yeah.
Feedback does not sound, that would ruin everything.
Yeah, I don't think so. But I think it'll all work out, so. We might start like 2-3 minutes. If that's all right. Yeah.
So say hi.
Good to see you,
How's it
man.
going?
How are you?
Good, good. How's the workshop?
It's coming along. A
Yeah.
lot of hiccups because of the AV system's a little bit difficult to get working. But yeah, but we're hanging in there. Yeah, we should get dinner or something, eh?
Yeah, let's
Yeah.
do it. Let's do it.
Yeah,
I,
I've been-
I have your contact.
Yeah. When did you? I don't have WhatsApp.
I could
Do you have, you have my iMessage?
Yeah, yeah.
Good. Yeah.
When
did you
I
get
got
in?
yesterday evening. I'm extremely jet lagged.
Okay.
Man, I barely slept.
Okay.
But anyway, I won't get to it.
Yeah, we're gonna get started here. Yeah.
See ya.
Okay, man. We'll see you.
You introducing yourself?
Jules. Oh, it's me. It is me. It's me.
If there is no way to play audio from your laptop in the room, then that's how it is, right? There's nothing.
I think this is gonna work fine. What was I gonna do for the? Okay, the other lightning talks are fine because they're all muted anyways. We're good. We're good. Yeah.
If one of you manages the spotlights and all you do is between spotlights, like say, you just call up the next person, right?
We only have the
Yeah.
titles of the paper. We'll just say
Yeah.
next paper is, yeah.
Yeah, you just call them up and help them set up and manage a question in between.
Yeah.
For the last one, between the second to last and the last one, tell all the lightning talks to start lining up there.
Is lightning talks? Is that right after Matthew Stable?
We should probably go ahead and get started.
But
soon.
it's Matthew's talk, spotlights, lightning sponsors.
Yes, exactly.
So
But
during,
if
for the last spotlight, just start telling people to line up in the order that you sent it out already. And they'll walk up on the stage, present, and walk off.
yeah, but if they cannot join the Zoom, that's a bit of a problem.
Wait, why, who needs to join the Zoom?
The lightning talk,
The spotlight presenters,
Wait, I just sent an email to all of them.
but they're not the people that are necessarily presenting. So I need to find those people.
I think
see.
one of them just came up to me and I sent him the link for joining. So data mill's covered.
Data mail's covered.
Data mill's covered.
Did you send to
I
GFA
sent to Jaffe.
Uh-huh.
So Moact is covered.
and Wolf?
I
Boy,
sent- I
did you
sent-
send to Boy? Yeah,
Yeah,
probably
it's there.
it's the main, and then Nerf Hog is this guy named Daniel Ekbo.
Okay, let's go find him.
Yeah. Oh, it's okay. It's okay.
okay?
Yeah, we have it figured out.
audio?
Yeah. Should be okay. Yeah, thank you. Okay, everyone, we're gonna get started. Before the first talk, if you're a spotlight presenter, could you please come to the first row? Thanks. All right. So we have a talk. We're here joined by Matthew Marge. Matthew Marge is a DARPA program manager as of January 2023. He joined to create, execute, and transition programs in artificial intelligence, human-machine interaction, and multi-agent systems. He's an adjunct professor of linguistics and computer science at Georgetown University with over 50 authored or co-authored publications. Matthew, please take it away.
Thanks so much, Chris. Thanks for Joey for hosting. So everyone, good morning to you all. I'm here to talk a little about one of my new program efforts at DARPA that's looking to create new investments in AI. And I'm here to actually, my goal in the next 15 minutes is just to get your feedback and thoughts on potential challenges we'd like to identify for this new effort that's called AI Forge. And I'll spend a few minutes talking a little bit about DARPA and then get into a little bit more details about this, the new initiative I'm leading called AI Forge at DARPA. So many of you have heard of DARPA before. It's part of the Department of Defense in the US government. Our main mission is to create and prevent technological surprise. It was originally created in the 1950s in response to the launch of the Sputnik satellite. You can see some pictures here of DARPA's greatest hits. You see in the middle, the DARPA, DARPA Urban Challenge, DARPA Grand Challenges back in the 2000s, 2010s. And then, the DRC, DARPA Robotics Challenge, mid-2010s that did a lot of humanoid robotics. So as I mentioned, our focus is on creating breakthrough and paradigm shifting solutions in technology. That's our kind of space in the research and development ecosystem. And we work at the highest levels of risk tolerance in the US government. So we're looking at trying to tackle the highest risk, high reward challenges and solutions. And looking to create disruption and in terms of the investments in fundamental research, what are the disruptions needed to change the field of whatever technology we're targeting? So in the case of robotics, there's a lot of mainstream focus and interaction on foundation models. So what are the opportunities for disruption? So what are the focus areas that have implications for national security, for example? And there's 6 technology offices at DARPA. I'm part of the Information Innovation Office, where we lead mainly the work in AI and cyber. So you see there are 4 main thrust areas on transformative AI, offensive, defensive, cyber, fighting in the information domain, and resilient, adaptive, and secure systems. And I'm part of the cohort of the AI program managers at DARPA, where I create and manage programs that are multi-million-dollar investments in AI. So now I'll take a moment to shift gears, talk about AI Forge as a program.
So this initiative is something that I developed over the course of the last year and a half, really to explore ways that we can create breakthroughs in AI for national security by creating basically a forum, an industry university and government forum, where we want to partner with a lot of the frontier AI labs you hear about in the news, all the big companies, in ways to kind of cost share in that. And it's also a partnership with the National Science Foundation, so I'll talk a little about it. So here's our main, structure on AI Forge, a little bit about the program. So the basic premise is to stand up an industry, university, government forum to create breakthroughs for national security. And AI Forge is strategically aligned with the AI Action Plan. You might have heard about the AI Action Plan from the U.S. government and the Office of Science and Technology Policy. We're partnering on this effort with the U.S. National Science Foundation, not only as a co-sponsor, but also an operational partner that can take over the responsibility of running this forum once it reaches a steady state in a few years. We want ultimately in this forum to combine the talent from universities with the capabilities and resources from the frontier AI labs to create national security focused AI innovation. And also ultimately to create an ecosystem that catalyzes innovations in AI for national security and fosters talent and idea exchange more freely between the frontier AI labs, government, and universities than today. So I'd like to talk with you today a little about the structure of this program and get your thoughts on what you think could be good ideas. And this is where I want to open up for questions and comments on what kind of challenges you see in the field of robotics, and especially in this workshop on data collection. What are the implications and challenges we should prioritize internally with this kind of effort? So the centerpiece for AI Forge is to bring on a nonprofit to serve as a forum manager. That's what's in the middle of the slide here. And the AI Forge forum manager will execute and manage a series of what are called project ventures, which are high risk and fast paced university-led efforts that are basically a year or less in duration, trying to tackle a challenge at scale. In this case, each project venture, we're going to be launching dozens of these project ventures, but each one is meant to tackle a critical AI challenge for national security. And this is where I want to get your input today on what do you think should be critical challenges. And within the AI Action Plan, this program is essentially aligned with the effort to advance research in AI interpretability, AI control, and adversarial robustness. So I think one thing I'd like to bring up in terms of when you think about topic areas and themes, what advances those three areas for AI, especially robotics and AI. And each of these kind of each project venture is supposed to tackle a kind of a shared or cross-cutting problem across the industry. And we want to tackle ultimately what we consider pre-competitive or pre-commercial AI research in this program. And each project venture is trying to tackle things at high scale, meaning demanding high compute or use of frontier models. So many universities today have trouble getting access to the level of scale that the frontier labs have in terms of either compute or frontier models, and we want to enable that to be possible in this program for universities. So let me talk you through some of the pieces of this program in terms of the elements. So universities bring the core talent to this forum, ultimately in the form of faculty, grad students, and postdocs, being able to now do things at scale with the resources we want to with the resources that we plan to have being offered by the frontier labs. And the frontier labs, we're talking to all the major players here in forming this forum, are looking to provide insights into critical AI challenges based on their own internal forecasting. Ideally, liaisons from those companies can be partnering with some of these project ventures and offering up resources in the form of frontier model credits and compute. And for national security stakeholders, we're thinking, folks across the government that would want to be tracking these kind of project ventures in the U.S. government, offering up insights into national security challenges to shape project ventures and use cases, along with operationally relevant data. And in addition to that, universities are now being, with this forum, about enabling them to tackle a lot of things at scale. With the frontier labs, it's about incentives like accessing shared intellectual property or shared IP and early access technology. And then for national security stakeholders, it's about getting access to demos and prototypes. So let me just kind of reflect a bit more. This is the only slide I really have in in this presentation. I want to have a little bit of time for discussion, but my main question for you all is sort of, what do you think are some of the critical challenges in robotics that are focusing on AI interpretability and AI control for adversarial robustness? So yeah, and I can also take questions about the program itself. So let me stop there and take questions. Thanks very much. Yeah. Yeah, so my contact information is, you can find my email address there. All right, thanks very much, everyone.
All right, everyone, now we're gonna start the spotlight talks. So we have 4 spotlight talks. The first is from Wolf, which is about capturing with this happened with the world's summer management framework. So we'll have 4 spotlight talks, and then all the lightning talks will begin right after that. So if you're giving a lightning talk, towards the end, we'll give you another reminder that you can line up in order that we then have. Thanks so much, and we'll start the spotlight talk.
Okay, hi everyone. It's my great honor to give a presentation about our work, WOF. So as we all know, for robot learning, the auto labeling is a very critical task for us to do. How we annotate good data is a really important thing. So this work, we aim to try to understand from video and caption everything that we can learn from the video and use that to build the labels for any robot videos. So that's our name, captioning everything with a word summarization framework. So as you can see from this is a video, autonomous driving videos, and we basically want to annotate what is happening and how the car moves. And so the reason we propose the work. In summary, it's a mixture of experts that will take the usage of both video level model and image level model to annotate the car's movement as well as the scenario description. So here is a WOF example. And the WOF not only can provide annotation for autonomous driving, but could also for robotics and the general things. To evaluate this, we also create a benchmark to evaluate all these scenarios. And we also design a CAP score to base the evaluation matrix to evaluate how the annotated labels aligns with the real world videos. And we also conduct a validation study to evaluate the validity of the CAP score with the human evaluation score. And in summary, WOF achieves much better results based on this mixture of expert framework. It outperforms GPT-4V and Gemini Pro 1.5 in this motion captioning. And here we give another example. And this is our WOF's caption, and you can see it can successfully capture the car's motion as well as the scenario. And in summary, we designed the first word summarization framework WOF for video captioning, and also the based metric CAP score. And we also introduced both benchmark and 4 human annotated benchmark data set. And the code data and the leaderboard has been open source recently, and we will continue the efforts and improvements to refine the WOF data set. And just now I talked about the WRF V1, which is the submission for this workshop. But now, through this opportunity, this is our first time to announce our WRF V2. Basically, we propose a very advanced, I believe it's a soul tower model that to annotate the motion information in any robot videos. So for example, this is all the results here are zero shot. So basically, we just randomly take any robot videos, and our model is able to annotate each object as well as how each object moves. And also, we automatically capture what object, what hand is moving, and then we track that object and describe and also annotate the semantic information with the movement. And all these things are zero shot. And the technical detail will be released soon, but in general, our model is trained on basically the general videos. It's not specifically for robot videos, but it can be generalized very well to robotics. So thank you very much. More information and the leaderboard will be updated. Thank you.
Thanks so much for the great talk. We have time for one question, actually, if anyone has a question they'd like to ask. Otherwise, I would ask, how do you determine which objects are relevant for manipulation within C?
Yeah, so basically for the demo is just to show, basically we automatically detect what object is moving. How we detect that is based on the object's movements. We track the location of each object in every frame, and then we can identify whether the object is moving. If the object is moving, then we will start to track that object and to identify that movement.
Thank you so much.
Thank you for your great question.
Our next spotlight will be my mobile fair.
Oh, okay. Yeah, hi, Ram. My name is Jia Fei from the Institute of AI and also University of Washington. Today I'll be presenting Momo Ads. So I think we have seen a huge success with open data model, especially coming out from, I'm not sure why is it weird. Does this work? Okay. Yeah, coming out from AI tool with Momo, and Momo has sort of pushed the boundary of pointing capability, developing frontier models, and you have seen that many of these frontier models start to develop pointing capability. In fact, this is really useful in robotics, for example, providing good priors for automating robotics foundation models. But the question is, can such spatial representation go beyond pick and place? Can you tell Momo to generate a plan, a trajectory plan to sort of steer the policy to be able to execute this task or pour me a cup of tea? And beyond that, we need to have some sense of depth to be able to reason over our action. Maybe I just share this. And is reasoning over action via language actually sufficient to solve the task? Giving GPT-5 this task and this instruction, you're not able to get a prompt that's able to solve this task. And with that, we introduced Momo Ads. So Momo is an autoregressive model that's able to take in observation and language instructions, perceive it, and generate perception token in a way that when it's decoded, it's able to represent in this kind of depth map. And condition on that, we generate visual reasoning trace, sort of act as an intermediate plan for the robot to take on. And when you decode this, you actually get a visual sketch of the next time step of what the robot actually wants to do. And condition on all this, you're able to actually output the necessary robot control action in order to solve the task. And from our pre-training evaluation of Momo, we are able to achieve some of the state-of-the-art performance on simple benchmark, which reflects the distribution of the OXC dataset. And in fact, we are actually able to achieve this with much lesser data as compared to the other models from physical intelligence and also from NVIDIA groups. So the secret comes in the data, similar to this workshop. We decided to use open source data, but their quality and quantity are just not good enough. So for just some context, you can see this kind of data say OpenX embodiment, with real instructions, even for like a whole 9 seconds, the robot is not moving at all, or even, the robot doing random things. And this is not the kind of data you want to use for training. So we started by actually filtering the entire OXC data set coming down to only 3 data set with over 190,000 trajectories. And beyond that, we collected our own high-quality mid-training data set called Momo data set. This contains different tasks in different household settings, even atomic skills. For example, how do you place a plate in an upright position, and also non-comprehensive skills. The key idea of Momo data set is focusing on high-quality demonstrations with repeatability. So each of these 100 tasks has over 100 demonstrations. And even by doing this, we are still far away from large-scale robotics foundation model that is training on a huge amount of robotic episodes. So how do we bridge the gap? So in LLMs, they use intermediate chain of thoughts to do reasoning, but reasoning in language is ambiguous for motion and space. So Momo proposed a new idea of robots should be able to do reasoning in space. And the way we do it is by curating data in a specific way to generate this action chain of thoughts that can be grounded. So we use Momo to generate all the points, and connecting all these points, you'll get a trajectory of what the next time step the robot should take. And beyond that, you want to reason beyond just 2D pixel, but a lot of this data doesn't have 3D. So we have to have somehow implicit 3D. So we use this idea of perception token to actually decode and label the RGBD image with this perception token that represents depth. And putting all these together in an autoregressive way, you get the action reasoning data set that sort of empowers Momo's reasoning capability. And we also incorporated other kind of data set to have the general vision reasoning capability. And Momo has 3 stages of training: pre-training, mid-training, and also post-training for different applications. And we're able to do reasoning in space, which outputs action, or we're also able to steer Momo in a way. And for post-training evaluation, Momo, as compared to all the other autoregressive models, we achieve state-of-the-art performance and also compared to reasoning-based models. And beyond that, we're also able to show that Momo is able to generalize to many downstream applications, real-world tasks across different embodiment. And okay, oh, sorry. Okay. What? Okay. By the way, let me say and go over this. I might not be able to post that. Anyway, yeah, thanks for everyone. I think hopefully feel free to ask me any questions.
So much. We have one question if anyone has one. No, there's no questions. I wonder how estimating errors is sort of like the point detection or the depth estimation, like you pass the model.
Yeah, so I think definitely those will affect the model, but because we are focusing on large scale pre-training, so a lot of these are counter learned in an implicit manner by the huge amount of data. Obviously not that much, but yeah. Thank you.
All right, thank you. I guess talk will be on data.
Oh, okay.
Should be good. That's good. Yeah.
Hi everyone, this is Satish, and today I'm presenting this exciting work data mill on behalf of my colleagues at UT Austin. So recently, the robotics community has collected a lot of large data sets with varying embodiments, scenes, and tasks. Now, suppose you want to train a policy on a target task, and you want to use this data to improve the performance of these policies. So given the messy nature of this data, it's unclear which data would be actually helpful for a task. Some samples would be helpful, while others could be harmful as well. So how do we select the right subset for improving policy performance? So prior works tackled this problem by selecting most similar data from as the target data set based on some heuristic measures such as motion similarity or visual similarity. While intuitive, this can bring data which could hurt the policy, and it could also miss out on valuable data which could be helpful to the policy. In reality, what we want is this weird purple blob, or more accurately, what we want is to find a subset from the data that maximizes the performance of the policy on the target task of interest. So given this intuition, let's make it more formal. given a data set B, a learning algorithm A that maps data to a trained policy, and a performance metric, which in our case is the success rate of policy rollouts. We want to obtain the data, the subset of the data that maximizes this performance metric. So directly optimizing for this objective is hard because it requires you to train policies for every possible subset of your data set. So in order to solve this issue, we use the data models framework. Now, what are data models? At a high level, data models try to approximate the metric as a function of the data. Under the hood, what these methods do is they try to measure the positive or negative influence of each sample on the performance metric. Thus, it's directly allowing us to measure the usefulness of a data point. So I won't get into how we learn these data models. You can check the paper for that. But two key things to know is that there are estimators which require several passes over the true performance metric. And the second key thing to know here is that it's much more efficient to obtain data models than training policies on every possible subset of the data set. So in order to adapt the data models framework to robotics, we introduced several key challenges. The first one is recall that data models require computing several times the true policy of the true performance metric, which in the case of robotics would mean costly rollouts, which is not feasible. Therefore, we use a proxy metric of validation loss on held out target data instead. Further, we also use sub-trajectories instead of using single data points to make the estimation of data models less noisy. And we also introduce a co-training recipe, and I'll not get into the details of those two in the interest of time. We evaluate data mill on the challenging setting of data selection from the messy OpenX embodiment dataset. And one of the key results that I want to highlight here is this result on cross-embodiment transfer. So here the target data that you can see on the right is with a Tiago robot, and the Tiago robot is not at all part of the OXC dataset. So this is a completely new embodiment, and we find that even in this case, the data mid framework can allow us to select relevant data. And this shows that the true finding this data selection problem is much more nuanced than just doing visual similarity or motion similarity, because you can use data from very different sources as well, and it leads to positive transfer. We also evaluate on multiple target tasks together, and we find that in all cases, data will outperform prior methods which are based on heuristics. In summary, we introduce a data model framework, which is a more principled way of viewing data selection. And in data mill, we introduce several key adaptations which make the data models framework work for robotics. Finally, we show across real world and simulated tasks that data mill outperforms prior heuristic-based methods. That's all.
We got time for one question. Okay, if not, I have a question. So in data mill, you're using the validation loss as a sort of attribution target.
Yeah.
For selecting data.
Yeah.
The validation loss is sort of surrogate for the closer performance of your policy. I'm wondering if there are some quantitative trade-offs between doing attribution on actual rollouts versus the validation loss.
Yeah, this is sort of the question that we expected, right? Because a lot of critics on whether validation loss is a good metric. So we actually do evaluate and do experiments in our paper where we start with actual rollouts, and we compare the performance difference between using the proxy measure of the validation loss versus using the true real world rollouts, and we find that the performance drop is very small in this case. So it appears in our case, in the data selection case, it seems like a good enough metric.
Thank you very much.
Thank you.
All right, hi everyone. My name is Daniel, and I will be presenting in behalf of the authors. NERF is a novel approach to augmenting existing robotic models to work on novel objects using neural reference fields. In imitation learning, an expert controls the robot to perform a task, creating demonstration to train a network to mimic those actions. And this works. Okay, yeah. This worked for the original task, but often fails to generalize to new objects. While collecting more demonstrations for each new object might help, it is not feasible at scale. Existing methods use pre-trained diffusion models to augment the training dataset by inpainting a new object in the position of the old one. However, this approach has some limitations. They inpaint objects with the wrong size or orientation, produce framing inconsistencies, and are slow due to iterative denoising. We instead use nerve models, which are faster, more photorealistic, consistent across frames, and support a wider range of viewpoints. Our method has 5 steps. First, we build a nerve of the new object. Second, we compute camera poses for each frame. Third, we use the nerve model to render the new object views. Fourth, we erase the old object with an inpainter. And finally, we blend the nerve renders with the original video frames. This slide has an overview of the method shown. And the animations following demonstrate the steps. First, we segment the original object using a video segmentation model. And second, we erase the original object of interaction. Third, we use a robot gripper to create a nerve model of an object we want demonstrations from. Fourth, we use a trained nerve model to render the nerve object in the position of the old object. And finally, we combine nerve renders with the trajectory in images to make a highly photorealistic synthetic dataset. Here we show our method versus other methods when it comes to augmenting the same demonstration. We also show that our method can properly grasp the blue box while other methods are not able to do that. By generating highly realistic synthetic data, our method generalized to novel objects with high success rate. And even with having to train the nerve models, we still find that our method is able to augment data much faster than the baselines.
Questions? Okay. What if the objects are in quadrant? Do you have trouble with the segmentation there?
That is a good question, and I believe in some cases, yes. I mean, the use of the shelf object detectors, like grounding dino, etc. And so those are robust enough in some cluttered situations. But if it's too cluttered, I think they would fail.
All right, thank you so much. Then I move on to the main talks for all of the posters. So if you have one, please line up your one on the right hand or left hand side of the stage. And Chris will be managing the video. So everyone with a lightly talk, please head up to row one and we'll get started shortly.
Everybody else, they're
Okay. All right, we should be good to start. Starting with demo speed up. Okay, click it when you're ready to start, and then
Okay.
video.
Okay. I'm Zhenrong from Tsinghua, and I'm glad to present demo speed up, accelerating visual model policies via entropy guided demonstration acceleration. Are you tired of robot videos with 5x acceleration rate? To make robot work like humans, we believe fast human speed execution is very important. Therefore, we propose demo speed up, a self-supervised method that allows you to train fast visual model policies from slow demonstrations. A key insight here is that not all the frames in a demonstration are as equally important for a task success. Frames with higher action entropy correspond to more casual sections and therefore can be more safely accelerated. Demo speedup can be applied to arbitrary generative policies such as popular ACT or diffusion policy. We found demo speedup can boost the execution speed by up to 3 times while maintaining or even boosting the task completion success rate. Thank you.
So hi, I'm Zifan from New York University. Excited to present our work, Touch Begins Where Vision Ends, shines with policies for contact-rich manipulation. So a lot of times, such as this, USB insertion is very difficult for robots because it requires millimeter-level scale precision. And that's the reason why we propose our vital visual tactile local policies that integrate egocentric vision and tactile sensing to achieve precise manipulation within just 3 demos of behavior cloning and 45 minutes of online reinforcement learning. And we can achieve different spatial generalization and also visualization to different kind of backgrounds and robust to different distractors. As you can see, it's doing a precise insertion task here. Yes. And also we found that tactile is very important for all kinds of contact-rich tasks that is helpful for the manipulation. And here is the live demos for us doing the real robot routes. And if you're interested, feel free to visit our work on our website and check our code. Thank you very much.
This is not my.
Yeah. What number are you?
I'm 4th because there was a miss, I guess. I'm collage.
Let's get this one then.
Hi everyone, I'm Satish and I'm back again, this time to present collage. So we want to train specialist policies without having to collect lots of new data. Data retrieval methods enable this by starting with a small scale target data set and finding from large scale data sets data that is similar to the target, and then they co-train with the target and retrieve demonstrations. However, current approaches for data retrievals rely on a single modality for retrieval, such as visual, 3D, or motion similarity. However, relying on a single modality can be limiting as different tasks benefit from different types of cues. In collage, instead of committing to one set, we retrieve data using different modalities and then predict a weight for each modality based on its relevance to the target task. I know there was a lot of details in the slide that I didn't cover. If you want to know more, please visit me at the poster. We achieve around 57% performance improvement with collage and on real world tasks. Thank you.
Hi everyone, I'm Lauri Suomala and this is a work titled Synthetic versus Real Training Data for Visual Navigation. Sim-to-real gap is a well-known issue in robot learning and several prior works try to quantify the width of this gap. A question that has remained unexplored until now is how the sim-trained policies compare to ones trained with real data. This work studies the issue in the context of topological navigation. We train a navigation policy on real data, another version of the same policy on simulated data, and we compare both policies on a real robot. And here you can see an example of a turtle bot navigating with the sim policy. We find that with enough training data, the simulation trained policy can outperform the real data trained counterpart, and the previous SOTA to handle real data. Vision encoders pre-trained with large-scale datasets and on-policy learning are crucial for the sim-trained policy's real-world performance. Thanks for listening, and see you at the poster. Okay, I'm Xudong from SaaSTech, and we present the Magic Cloud. Okay, I'm Xudong from SaaSTech, and we present Magic Cloud. Magic Cloud is a two-finger effector, and it can be handheld or mounted on a robot arm. It captures action data from real-world demonstrations, and the third finger can feel the force and 3D shape during the interaction. We use ISAC to provide 6D pose and RGB data. All data can be visualized through a web-based interface. Human can use Magic Cloud to teleoperate a robot arm and can physically feel the force feedback. And we use Magic Cloud to collect data for multiple tasks, both single arm or dual arm. And we also use Magic Cloud in a simulation platform like RoboSwift. So that's all. Thank you.
Hi, I'm Daniel, and I'm presenting IVE. Humans are naturally curious. Through exploration, we learn about the world's dynamics. How can we get robots to explore autonomously without extrinsic rewards? VLMs can reason about what objects are, where they are, and what might happen next. However, when operating independently, they rely only on imagination and prediction. On the other hand, humans are motivated to discover new scenes. Driven by curiosity, we use semantic understanding, structured reasoning, memory, and action to explore. Inspired by this, we present Imagine, Verify, Execute, or IVE. IVE is an agentic system that helps VLMs explore more like humans. It represents a step toward more grounded and semantically guided learning for embodied agents. Thank you.
My name is Shizhe. I'll present our work, Guardian, detecting robot planning and execution errors with vision language models. Robots often fail. It's critical to detect these failures for recovery. The existing work mainly rely on limited data and single images, leading to poor generalization and low precision. So in this work, we propose a Guardian, a fine-tuned VLM for failure detection. It combines multi-view high-resolution images and language reasoning to improve the failure detection accuracy. We also propose an automatic failure data generation pipeline to train Guardian. We perturb successful robot trajectories in both simulation and real world to generate diverse failure cases, including planning and execution errors. Our model achieves state-of-the-art performance in both in-domain and out-of-domain benchmarks. For more information, please check our poster. Thank you.
Hello, my name is Archer Kremshin. I'll be presenting task robustness via relabeling vision action robot data. While robotics manipulation datasets remain small due to difficulty of collection, with language diversity especially lagging behind. This often leads to robot policies that can perform tasks in new scenes but struggle to follow language instructions, often defaulting to visual cues instead of the text commands. Our work, TREAD, systematically augments existing datasets with greater language action diversity without collecting new data. Using VLMs, we 1. Decompose tasks in semantic subtasks, 2. Identify temporal boundaries in the trajectory videos, and finally, generate grounded paraphrases incorporating object attributes and the spatial relationships. We test on 2 scenarios, language generalization with linguistically modified tasks and motion generalization with new instruction scene pairs. The results show TREAD improves both planning generalization and language following, achieving gains without any additional robot data collection. Thank you.
Hello, everyone. I'm Amir. I'm presenting our latest work for data generation. Our NICE framework is a generative model or generative pipeline that performs the different manipulations on existing samples. And it can basically scale the data without any human involvement. We done a number of experiments to show the resulted data is very realistic comparing to real world collected data. And also we show that fine-tuning our data can significantly improve affordance prediction, and as well as the manipulation tasks when we is evaluated under different cluttered environments, and it can improve the robustness and generalizability as a result. Thank you very much. If you're interested, drop by the poster.
Okay, just let him make it easier.
We present GRIM, a framework for task-oriented grasping. GRIM's full form is grasp realignment via iterative matching. There are a lot of grasping data to learn from, but only a fraction is task-oriented. This requires for a data-efficient method to learn generalizable grasping that generalize over tasks and objects. To tackle this problem, we present GRIM, a training-free framework that conditions grasping on generated videos. We first use reference, image, and desired task to generate a video of desired grasp, then reconstruct the hand-object interaction, saving this hand-object interaction into a flexible memory. During testing, we exploit this memory, but to retrieve similar objects and align it with the scene to efficiently transfer the graspers. Although we demonstrate real robot application on paddle gripper, our approach is easily adaptable to dexterous hands. To find out more about them, you can scan the QR code. Thank you.
Hi guys, in this work we present two-handed afforder for learning precise, actionable bimanual affordances from human videos. Most affordance prediction methods typically reduce the problem to part segmentation or direct object segmentation. Instead, we propose a pipeline to extract these task-oriented affordances directly from human video sequences. We use mask propagation and so on, and we get a data set to which we train VLM-based segmentation in order to get both bimanual segmentation masks for the left and right in a task-oriented manner. And we see that our work works better than a bunch of the other baselines that are there, which do either full object part segmentation or aren't able to localize the object properly. And with this, we're actually able to use more actionable grasps that robots can execute based on the task that they need to perform. Thank you.
Hi guys, I'm Jiwon from Hyundai, and I'm here to introduce a way to scale your dataset without robots. We create dataset directly using hands with a VR device. So first, we start by locating a robot base in the VR coordinate frame. This is used to transform hand trajectories into robot end effectors. Next, a human naturally performs a task. And then we add gripper state and action to the collected dataset using VLM and multimodal filtering. And then to address the visual gap, we replace human hands with robotic hands in the observations. To verify our dataset, we use a custom dual system VLA, and the results show that faster data collection and boosted policy performance. Future works will focus on minimizing the domain gaps. Thank you.
Hello, everyone. I'm Greg Wolke from Zoox, and I'm going to be telling you about a reward-driven method for scoring agents by relevance to autonomous driving. Humans are very effective at focusing on what matters in a scene and ignoring irrelevant information. We'd like our robots to do the same. In this work, we use a pre-trained driving policy, a driving simulator, and a driving reward function. And then instead of training a new actor to drive, we train an actor that seeks to mask out as much of the driving policy's input as possible. And then we can leverage the existing driving rewards to find the maximal set of inputs that we can remove while still getting good driving behavior. If an agent is not required to drive well, then that agent is not relevant to the driving task. In these examples, we can see agents marked with these colored dots are considered relevant, with the reddest dots being the most relevant. Yeah. Please come by our poster or read our paper to see more quantitative analysis. Thank you, everyone.
Hi, I'm Yuqi. I'm going to present Caesar, a self-supervised approach to data curation for large-scale imitation learning. So robotic datasets are growing fast in the size, and such large-size datasets always contain bad quality data like suboptimal and redundant data. How can we curate the datasets to effectively enhance policy performance? We introduced Caesar, which first starts from the diverse data trajectories, and it can detect the suboptimal and redundant transitions, and then it creates the data to create a curated dataset. We then train like VLA models like Octoline and get better policies. So we apply the method to different like large size data sets like OpenX or Cirrus, and then we shows that it can like outperform other data curation baselines. We compare it with Uniform, with DemInf and Remix, and we show that ours is getting better policy success rate. And this is a demonstration about like real world rollouts on the Mutex dataset. And thank you.
Hi, I'm Haruki Abe from University Tokyo, and our research focusing on expanding the robot dataset by combining two approaches, cross-embodiment learning and offline reinforcement learning. Cross-embodiment learning means training a single model across a robot with different morphologies, and offline reinforcement learning, compared to the imitation learning, allow us to learn not only from optimal trajectory, but also suboptimal ones. By combining these two methods, we can train across a wide variety of robots while also use suboptimal data. This gives us the potential to significantly scale up the dataset. In our work, we analyze the advantage of this setting as well as the challenges it introduces. If you are interested, please come and check out our poster. Thank you.
Hi, my name is Bo. In this work, we study embodiment scaling laws. Embodiment variations are pervasive in the real world, and we want to understand how to learn from and generalize across diverse physical embodiments. We use our hypothesis is embodiment scaling laws, that training policies on more embodiments lead to better generalization to unseen ones. We use robot locomotion as a testbed and generate 1,000 robotic embodiments by varying geometry, topology, as well as joint-level kinematic constraints. We then train a single model capable of handling diverse observation and action spaces on random subsets and observed positive scaling patterns in terms of generalization performance. In particular, we noticed that scaling embodiments is much more effective than scaling data to enable embodiment level generalization. Our single best policy can be deployed on go-to robots with modified joint limits, as well as humanoid H1 in the real world with the training. We hope this work in locomotion to inspire us in other task domains. Thank you.
Okay, our role contrastive learning in contrastive in context learning with active memory for task planning focuses on LLM-based task plan. This is our proposed framework. From the environment, we can obtain task instruction. Then the LLM planner generates demonstrations. When the robot executes them, the outcomes are divided into successful or failures. These are selectively updated into active memory with our diversity array selector. The successful demonstrations are used as positive prompting to imitate the ideal behaviors, and failure demonstrations are used as negative prompting to recognize incorrect behaviors. In this way, the model can learn by exploiting the contrast between these two types of promptings. Thank you, and see you in my post session.
Hello. My name is Pen Cheng, and I'm from National Research Council of Canada. So here we are presenting this work on data modalities. Data drives robot learning, however, it's unclear how to structure good data. We study teleoperational modality and evaluate key components. So we do two tasks, wiping a table and turning on a lamp with 400 demos from Oculus. VR and happily in verse 3, we evaluate via the NASA workload and fine-tune on the GRP like the Octo model. So in comparison, we found that VR controller is physically and mentally easier, but it's less precise and more frustrating. The haptic controller is more difficult, but precise, which yields higher performance in this comparison. What I've found in this experiment is that tuning action horizon critically affects success rate. Mixing the VR and haptic data consistently yields better performance, and additional preprocessing is not always helpful. Thank you.
Yeah, so this is Yang Binghan from 45 Labs. So when we reach for an object, our eyes move first. Gaze reveals human intent, locking onto tasks, critical details before our hands ever begin to move. Our work captures this hand-eye coordination. We use Vision Pro for our capture device for its accurate hand and head pose. But since it doesn't provide eye tracking and raw camera access, we augment it with a RGB camera and an infrared camera, secured with a custom 3D printed design. With this setup, we built a data collection pipeline that synchronizes eye tracking, RGB image, hand trajectories, and head pose. So our dataset enabled the robotic perception system to not just see the world, but anticipate it. Yeah, thank you.
And how can help with data curation? In last month, we started to see a big rise in open source data sets being shared in the public. These fantastic sources of data often might contain some episodes that might contaminate the training pipeline. We show how generative volume learning used as a helpful proxy for fitting value or correlation. This allows us to spot episodes that could create issues during training. We have also run a comprehensive benchmark of multiple open source models, showing a big gap in performance compared to closed source. We share our benchmark and leaderboard where you can compare different models and datasets along with the code for reproducibility. Welcome new submissions, and we have hidden emails. Please see our OpenGBL space.
Collecting robot teleoperation data is too boring. Instead, we collect a large ego and human task-oriented data. Here, task-oriented means the human data has clear start, end, and focus on specific tasks, just like robot data. We advocate human-centric representation, which represents actions using wrists and fingertip key points. is an embodiment-agnostic representation that applies to any bimanual robot. We train a manipulation policy using the mixtures of humans and humanoid data. The policy predicts future actions as key points, which are then retargeted to robot actions. Empirically, co-training with human data improves the policy generalization across different background, spatial placement, and object appearance. It also enables few-shot policy transfer across different humanoid robots.
Hey everyone, welcome to our talk Grasp Factory, a large object-centric grasping dataset. My name is Srinivas. I'm a principal research scientist at Autodesk Research. In this work, we introduce a large-scale dataset of 6-ToF parallel jaw grasps for the Franca Panda and the Robotique 2-fingered 85 grippers. We also train a diffusion-based grasp generative model on the Franca Panda subset and show that training on large geometrically diverse dataset leads to stronger generalization in simulation and real world. The current state-of-the-art dataset is the academic dataset that contains over 10.5 million successful grasps for the Franca Panda gripper across 8,872 objects. In comparison, our dataset contains 109.3 million grasps for the Franca Panda and the Robotique 2 and 85 grippers across 33,710 objects. We also train an energy-based diffusion model and show that training on large diverse dataset leads to generalization across novel objects.
We'll be presenting our work on understanding sim and real code training for diffusion policies. Simulation is a promising way to scale up data generation in robotics. Our work and others have shown that code training for both sim and real data can drastically improve. But what is the best way to leverage simulated data? And what are the principles underlying sim and real code training? We conduct a focused study guided by these two questions. In total, our experiments span over 300 policies, evaluated over 50,000 trials. More concretely, we studied the early scaling laws of sim and real code training, the effect of distribution shifts and the implications on policy training and simulator design, and the underlying mechanisms of code training, such as sim and real discernibility and power laws that predict real-world performance. I won't be at CoRL this year, but luckily my good friend, collaborator, and lab mate Nicholas should be at the workshop. Make sure to chat with him at our poster to learn.
Latent action models have quickly become integral to the pre-training pipelines of leading vision language action systems, as they promise to unlock vast amounts of unlabeled videos. At the same time, most latent action models to date have been trained on relatively clean datasets, such as in static scenes with a single manipulator. In contrast, real-world data often contains numerous action-correlated distractors, including background human movement. In this work, we propose to utilize the common-sense reasoning abilities of VLMs to provide promptable representations. We benchmarked more than 10 VLMs and conducted over 14,000 experiments to answer the following questions. 1. Whether VLMs are capable to produce promptable representations? 2. What is the best VLM that can provide these representations? 3. What is the proper way to extract these representations from VLMs? If you are interested in the results, see you at our poster.
Autonomous driving systems are usually trained on incident-free data that shows good behavior, but offers little guidance on what to avoid. Real crash reports contain that missing knowledge, yet they're difficult to use directly. We address this with a pipeline that takes a driving scene and candidate action and grounds the decision in retrieved precedents. We use both safe and unsafe data to enable the system to reason about a candidate action. At the core is a unified encoding that converts both multimodal driving logs and crash reports into structured graph representations, making two very different domains directly comparable for retrieval. On top of this, we design reasoning engines that decode a query scene using retrieved precedents. The counterfactual variant goes further by proposing alternatives, evaluating them against precedent, and refining its judgment before deciding. This doubles recall of reasonable actions. From 24 to 53%, models tend to be overly cautious, but our method makes them safer and more decisive. Counterfactual reasoning improves decision calibration. Thank you, and please reach out if you have questions.
Introducing RAC, Robot Learning for Long Horizon Tasks by Scaling, Recovery, and Correction. Conventional data collection mostly demonstrates successes, thus learned policy struggles when facing RAC is a lightweight mid-training phase after training polyglot human intervention on failure. RAC has rules. First, you select an distribution region, then corrects to finish the step task. Second, terminate after the intervention. Training on RAC data composition teaches policies when to recover and how to adapt when going out of distribution. On short-hanging tasks, RAC achieves better performance than previous SOTA using 10x less training data. During rollouts, RAC policy consistently recovers from failures and reattempt to succeed eventually, demonstrating task time scaling. Success rate increases linearly with the number of recovery attempts and test time. For more details and videos, please visit our website.
The title of our paper is Beyond the Teacher, Leveraging Mixed Skill Demonstrations for Robust Imitation Learning. Imitation learning often struggles because the demonstrations we collect are noisy, inconsistent, and sometimes low quality. As demonstrated in the video, imitation learning methods fail to perform on this data. With too few expert demonstrations, the model can't fully capture what's important for the task, such as closure, symmetry, smoothness, shape preservation properties. To tackle these demerits, our approach begins by computing a demo utility score with multi-objective losses, allowing us to select the most informative demo. We then extract smooth canonical motion from the selected demo using periodic DMP. Finally, we refine the demos using an adaptive LSTM. This robust two-step pipeline enables data cleaning from noisy, non-expert demonstrations and produces reliable robot trajectories for real-world execution. As demonstrated in the video, our proposed approach tackles the demerits of noisy, non-expert demonstrations and generates clean, reliable robot executable trajectories for imitation learning methods.
In standard behavioral cloning, we map states to actions. But with limited data, this breaks down. Demonstrations vary in speed and often contain brief corruptions. Instead of learning from raw sequences, we reorganize data by what part of the task is being performed. We learn a progress variable from state alone, giving us a shared phase across demonstrations. This is discretized into bins. Within each bin, we compute robust summaries. The median state and median action act as stable anchors that represent common behavior. The magnitudes of these terms capture the typical strength of actions and the rate of state change, giving a sense of execution pace. Tangents of state and action describe the dominant direction of motion at that phase. To handle outliers, we estimate a trust score per sample using leave one out comparisons, filtering inconsistent behavior. All this is combined into a ribbon token, a structured descriptor of phase-wise consensus and variability. We use these tokens to correct corrupted labels and train a simple policy with a weighted behavioral cloning loss.
It like disconnected and reconnected, so it's.
Oh, you should put it down and then like yell into it. I don't know.
It's here.
Yeah.
Then, do I? Share. No, this is live stream. Yeah, that's fine.
You don't share.
Yes.
Wow. You can exit Zoom and share your screen and share there. So be on the live stream.
Sorry, what's the link?
Oh, I sent you an email. I think I sent you the right email address. Yeah. There you go.
And turning off audio. Grab a picture. Is the mic gonna be on?
Yeah, the mic is on.
Yeah.
It's early.
Can I have 18 minutes?
Yes.
Okay, precisely.
We have
I will try to.
no worries. They said really appreciate it. This is great time. Which actually really appreciate.
I kind of like it. I just need
I assume during the time. Okay.
Not right. Okay, pass it over. That'd be great. And also, like, the slides are not right, like, right there, they're really far.
Hi, everyone. Welcome back to the Data and Robotics Workshop. We're going to go ahead and get started with the afternoon talk session. Our first talk is going to be from Masha. Masha is a research lead and manager in the Large Behavior Model Division at Toyota Research Institute. At TRI, she co-leads the Trustworthy Learning Under Uncertainty effort in the context of robotic manipulation. Her research focuses on policy evaluation, failure detection and mitigation, and active learning. Previously, she finished her PhD at the Stanford Intelligent Systems Lab on uncertainty-aware perception for self-driving cars. Her work has been published in top-tier robotics conferences and machine learning conferences, including RSS, CoRL, ICRA, and NERV. So with that, let's have a warm welcome for Masha.
Thanks, everyone. How's everyone doing post-lunch? Still awake? Yes. Great. I love that enthusiasm. I'm going to talk about trustworthy learning under uncertainty for robot data, and conveniently, Joey already explained this slide. I totally tell you. We focus on evaluation, failure detection, and active learning / adaptation, and I will talk about some of these today. All right. So we've all seen really cool results from a bunch of different companies showing policies that can perform really dexterous tasks, long horizon tasks, can generalize to new manipulants, high precision, like TRI. This has all been really exciting. The success of all these models is highly dependent on data. So there's been a lot of open source and internal effort to scale this robot data, right? The video I have planned here is from Droid from a few years ago. And that's great. So great that TRI has recently put out an LBM 1.0 paper where we really set forth to rigorously evaluate whether this data scaling hypothesis is actually true. And spoiler alert, it is. So we found with statistical significance, on the left, we have simulation, and on the right, we have hardware. From these plots, we can see that scaling the data scales the performance. And the way that you can tell that it's statistically significant, these are called CLD plots. Basically, the alphabet tells you whether it is or it isn't statistically significant. So if you look at the left plot, you see A, B, B, C, D. Whenever you have a different letter, that means those two lines are statistically separable. And as you go up in this plot, you have more data. So you can clearly see the performance gains both on the left and on the right. That's great. One important type of data that's often overlooked is failure data, right? All these models, none of them are at 100%. And especially when we start seeing robots go in the wild, nothing's going to be at 100% success rate. So in the context of failure data, autonomously detecting these failures starts to become important. And why is that? Well, we could do a bunch of things with failure data. The most obvious one is safety monitoring, right? When we deploy something, we want to make sure that we have checks and balances for when things start to fail or have failed, and we need to figure out how to get back to nominal conditions. Failure detection also tells us about the limitations of the policy. The more positive view on failure detection is it can tell us what new data we need to improve the policy. It can also help us learn models of the environment or world models. It can tell us when to switch back to a different policy when we're in a weird state. And it can also tell us if we see failure rollouts, can we actually bring this back to the data and curate the data so that we have mostly successes. One point I'd like to make here that I feel pretty strongly about is regardless how much data we scale, we're always going to have a long tail. We're always going to have that one weird scenario where something fails, no matter what. And we need to be able to gracefully and safely react to these failures, which includes first detecting them. So one bullet point I'd like to zoom in a little bit more on is this data curation idea. In the last year, so this is all 2025, there's been a serious uptick in the number of data curation papers, which is fun and exciting, but why? So the reason why is it actually helps us adapt to environments. So let's say we start with all this data in all these different environments, and then we deploy in an environment that's slightly different than what we've seen before. So this is a slightly different blue color than on the left. What we can do is we can roll out a lot of the policies in our new environment and then take that information back to tell us about the data that we already have. And we can then rank this data as most useful towards contributing to success versus least useful. And then take that subset of most useful data for success and retrain our policy and hopefully improve our success rate. So this environment adaptation aspect to this is really exciting. So with that, these are the two areas I'm going to focus this talk on. First is policy-aware failure detection, and the second is deployment-aware data curation. Let's start with the failure detection bit. This is a paper that was presented by Chen Zhu 2 months ago at RSS, and he did an internship with us a summer ago. So he developed this method called fail detect, and it consists of 2 stages. Stage 1 is learn a score that's reflective of successes and failures. An important aspect of this, and this is really key, is the input to this score learning model is a feature extractor that is trained in the loop with your policy. So that's important because this tells us not just about the observations, but the observations relevant to your policy. And the reason this is important is we don't care if we're in an in-distribution environment or an out-of-distribution environment. We care whether the policy is going to fail, right? And that can happen in either case. So I'm showing an example of in-distribution setting where we have a normal towel that's been seen in the data and the policy fails. And then the alternate, which is new towel, never seen before, but ends up succeeding at the task. All right. And then the score itself is just a proxy for a negative log likelihood that we estimate through some flow matching techniques. Next step is we have all these scores. We have to calibrate a threshold, right? A decision point. And we do this using successful rollouts. We don't want to overfit to any failures that are particular to our data set. We prefer to model success for this work. And so everything, demonstrations, rollouts, everything is just using successes. And then the full system just looks like that right diagram there. We compute a score as we go through a rollout. And if that score is above the threshold, we flag failure. And if it's below the threshold, then we stay as success. Great. All right, let's look at some examples. So this is RoboMimic. This is a square task. What happens here, I'll play it again. We have a slip failure detector reacts and says, hey, there's a failure there. This is transport, it's a handoff task. What's interesting about this failure, if I can zoom in on it, is the lid is thrown off. So the task has not actually yet failed, but the lid was out of frame and the failure detector reacts. And what happens afterwards is actually the policy messes up. So it fails to get the hammer because that visual observation messed up its policy. And then this last one is just a hanging task where it misses the hang and flags failure once again. Let's look at some hardware. This is a towel folding task. And we have an adversarial annoying human that's messing with the policy. So it is trying to fold, human gets in the way. And in this case, it messes it up. It misses this fold and failure is detected. Similarly here, we have a challenging crumpled towel initial condition with a distractor. And in this bottom scenario, it again misses the fold and the failure is detected. Let's give it a second. Here's the missed fold. There you go. I'll show a few more examples. So this is the coffee spill task that I showed at the beginning. The idea here is move the mug out of the way and then clean up the spill. And here we have a situation where it misses the mug. And so the failure is detected again. This one I actually really like, the failure case, because it misses the towel and it starts to put the gripper into the coffee spill, which could be dangerous for the hardware, right? And the failure is detected before that happens. And shortly after, the human intervenes because we don't want to damage their hardware. So great, we have this two-stage score learning, threshold calibration, and then we have a failure detector. The awesome thing about this, to me, the takeaway, is that this policy-aware embedding is really useful towards this failure detection task. But in this paper, we only tested it in single task models. So in our collaboration with the University of Toronto, we actually extended some of these ideas, now using both successes and failures, to VLAs, so multitask policies. So can we have one failure detector for many different tasks? This is going to be presented at NERPS and has been an awesome collaboration with the University of Toronto. So let's talk about SAFE. The takeaway is surprisingly similar from fail detect. So I think this is probably my favorite figure out of the paper. What this is telling us, it's a t-SNE plot of the embedding space of a VLA. And on the left, we see successes and failures. Successes are in blue, failures are in red. The failures are all clustered together in this space. And that's really exciting because in that same cluster, we have many different tasks. That means that we have hope to generalize using this embedding space to detect failures in new tasks that we haven't seen before. So what does this look like in the embedding space? The success you can see is sort of populating in this blue space and staying out of this red region. And a failure starts out in a successful location in blue and then starts to fail once it messes up right here. And then it suddenly goes into the red immediately. So that's really cool. The system itself is very similar. Outside of now including failures to calibrate and to learn the score, again, we have these two stages. We have a score learning stage and we have a calibration stage. And once again, this looks very, very similar with now the change that the task has not been used for training the score or calibrating the threshold. And on the left, we have a success, and on the right, we have a failure that as soon as it goes outside of this threshold area, it's marked as failure. Basically, the robot's just stalling here. That's why it doesn't look like much is happening. Cool. So the takeaway is this policy-aware embedding space, super useful and informative for failure detection. And it will hopefully lead us to a place where we can actually reliably detect failures in tasks we've never seen before. And I find the definition of task can be fast and loose. For example, what if we have a new out of distribution object that we haven't picked and placed before, right? That might be a new task. So being able to generalize to all these differences is very exciting. With that, let's talk a little bit about deployment-aware data curation. This is a paper by Chris and Rohan, who are organizers of this workshop as well. And they're going to be presenting this paper tomorrow. So come by if you're interested. I have the information on the slide. And this has been an awesome collaboration with Marco and with Jeanette and Rika and Stanford. So the idea is we start with some data, some demonstrations, we train our policy, and we have our rollouts. And these rollouts come with success, failure labels. So what we can do, like we talked before about this, we can send this information back to the data, and we can actually rate the examples in our demonstration data set so that they're most attuned to be successful in whatever our deployment environment is. So making this a little more visual, maybe we have mixed quality demonstrations that are not so great or are okay, and then we're seeing some mediocre performance in our policy. Can we make this better by manipulating the data? Here's the high-level idea. We start with our demonstrations, we have the policy, and this is the key right here. How do we predict this counterfactual question of how does the expected return change when we remove a data sample from our data set? And the larger this difference is, the more important that data sample is towards success in whatever deployment environment we're considering. I'm not going to go through all the math here, but give you a high-level intuition of how Chris computed this difference or this gradient. So the first is, this is essentially a policy gradient trick to achieve a tractable sum. And breaking up the parts of it, one, we have a Monte Carlo estimate, right? We take the expectation and we compute it through whatever number of rollouts we have with success failure labels. And the second bit comes from influence functions. And computing this tractably is actually from a work by Park et al. From 2023. So the basic idea is the higher this performance influence is, the better this demonstration is towards success. What I think is most exciting about this method is how effective it was. So I'll talk about 3 examples. The first is if we have mixed quality data regime, right? So if we have a mix of good quality data and maybe a robot teacher that's early in their training and the quality is not so good. If we just train this figure 8 task with all the demonstrations without thinking much about it, we get an empirical success rate of 36%, right? And you can watch it fail. Now, if we take away 2/3 of the data, we remove it, we retrain the policy, we get a success rate that's doubled. I get really excited about these numbers because I'm so used to seeing 5% differences, and this is doubled in performance. So that's awesome. Next scenario is this tuck box scenario. So we want to take a recycling bin and tuck it under a bench. The trick here is we have added weight to the deployment environment. So we have a weighted box in our recycling bin. And now we have a difference from our demonstrations. And in the demonstrations, we had 2 strategies. One was to push the box, and the second strategy was to pick it up and then just tuck it under. So we start by training all of it, and it chooses the wrong strategy because this strategy is probably easier for the network to just push it. 0% success rate. Goes to 84% success rate by removing half of the data. That's really exciting to me. And this last example that I'll talk about is this spurious correlation setting, where you have to pull out a book. And there are 2 strategies. One is if you have a stacked book, you want to pull this way so the book on top of it doesn't fall off. And if you have a single book, you can just pull towards you and nothing will happen. The problem with the data was you have a dark background whenever you had a stacked book and a light background when you have a single book. So during deployment, we had a stacked book with a light background, and the nominal policy had 44% success rate here. And you see the book on top of it fell. Now, again, taking away 2/3 of this data, it picks the right strategy. The book doesn't fall. Great. So the idea behind this work is that we're connecting policy evaluation, so the successes and failures that we observed in whatever deployment environment we have, back to the data set, and using that to adapt our data set to be maximally successful in the deployment environment. What was great about this is it requires as few as 10 rollouts and works, and it's performant across all these different data scenarios. So please come check out the work tomorrow when Chris speaks about it. In conclusion, we talked a lot about policy-aware failure detection, so that embedding space that's strained in the loop with the policy, and this deployment-aware data curation. So with that, I thank you, and I can take questions. Any questions? Yes.
Just great talk.
Thank you.
Just to get a sense of kind of precision recall on actually show kind of a lot of the.
Yeah. It's a little hard. So I would say in balanced accuracy, we were getting something like 70%, pretty reliably, both in hardware and in simulation. I would say that's probably where we're at. And there's definitely room to improve. But what I found exciting in the failure detection space was that it was consistent for simulation and for hardware. And we just kept getting the 70-75% accuracy, which is great. Problem is, depending on how you threshold, you can make those numbers go up and down. So it's kind of an iffy question. Yes.
Part of this one.
To
show this failure detection happens from the feature of the model. And it kind of means that model itself knows that it fails. Do you think it may work if you just like zero out this activation that's basically responsible for failure?
It's a good question. The question is basically if we zero out the activation that's responsible for failure. First, you have to figure out what activation exactly it is. The one assumption here is that the embedding space has to be not meaningless. So it takes a little bit of time for it to become meaningful and for the failure detector to work. So I would say that's probably a limitation. I think the question of how you figure out which activations are or are not useful towards the specific failure, and then if zeroing out would do anything useful or it would just break the policy, I think I'm not clear on. Thanks. That's probably fine, right? Thank you.
I think not that.
So our second speaker is Chelsea Finn. Chelsea is an assistant professor in computer science and electrical engineering department at Stanford University and a co-founder of Physical Intelligence. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. Her research has been recognized by awards such as the Presidential Early Career Award for Scientists and Engineers, the Sloan Fellowship, and the ACM Doctoral Dissertation Award. Prior to joining Stanford, she received her bachelor's degree in electrical engineering and computer science at MIT and her PhD in computer science at UC Berkeley. Thank you, Chelsea.
Great, thank you for the introduction. So today I'd like to talk a little bit about what I think are some of the bottlenecks in developing robot foundation models. And to set the stage a little bit, at Physical Intelligence, we've been working quite a bit on trying to build more powerful foundation models, specifically vision language action models. And so far we've been trying to do that along a couple different axes. First, we focused on trying to develop really capable VLAs that can do really complicated tasks. And so in the first 6 months of the company, we were able to develop a model that could be post-trained to do a really complicated task like unload laundry and fold laundry. Certainly one of the, probably the most complex tasks that I've seen a robot do myself. And then of course, because it's a generalist model, you can also find it to do other cool things as well, like being able to put eggs into a carton and fold a cardboard box. And then from there, we kind of felt like one of the big bottlenecks was generalization to new environments, because these models were still quite brittle when you put them in different environments or when there's something changed about the existing environment. And kind of in the following 6 months, we were able to develop a model where we could kind of put it into a home and have it doing something fairly reasonable, even though it had never collected any data inside this particular home and a number of other homes that we use in our testing as well. So now kind of with this stage set, what are some of the bottlenecks for further progress in these generalist models for robotics? There's a lot of bottlenecks, and I won't cover all of the bottlenecks that I think are the most important, but in this talk, I'm going to talk about a couple major bottlenecks. And the first is speed, and the second is large-scale evaluation. So first, let's talk a little bit about speed. There's a lot of very practical use cases that demand suitably fast policies, and this could be for a number of reasons. So first, some tasks may be time sensitive due to the patience of a person that is receiving something on the other end, or economic constraints like the need to turn over kind of a plane that's being has maintenance on it, or turn over a hotel room or something like that. There's also scenarios where we want to be able to fit robots into human workflows, and if robots are a lot slower than humans, then it makes it a lot harder to fit them into those workflows. And then there's also just some tasks that are dynamic enough to physically require a higher degree of speed. Now, in terms of trying to address this bottleneck, one approach is to potentially speed up policies post hoc. And we've done some work on this. That was at ICRA last year. There's also, I believe, a CoRL paper this year on this as well, that tries to kind of take an existing policy and then speed it up after the fact. But really, the root of the problem is the data. A lot of the data that we train policies on is kind of slower than we would like it to be. So can we collect faster demonstrations? We've recently done a little bit of work on trying to study whether we can collect faster demonstrations. And a couple years ago, we introduced the Aloha system, and it's arguably like a very performant teleoperation system. And it's likely kind of never asking with Aloha, but it's harder as using your own human hands. So we're just trying to think about trying to collect demonstrations faster. There's a couple of things that you might consider as kind of the limitations. One of them you might think about immediately is that humans, we have like 5 fingers, whereas robots, we often use kind of parallel jaw grippers with robots, and maybe that is what's leading to slower speed. But in my experience, it's actually not the limiting factor for speed. And so with this in mind, I think that one of the kind of challenges with the Aloha is you do kind of have to be controlling a different robot system. And what if the operator could just hold the grippers themselves? Maybe that could allow us to collect faster demonstrations. This brings us back to what's known as kinesthetic teaching. I dug up a video of myself collecting a kinesthetic demo on the PR2 almost 10 years ago now. And obviously there's also a lot of work before 10 years ago as well that was using kinesthetic teaching. And it is promising, but also has some challenges. So robot arms can be large and heavy, like this PR2 robot arm. Human arms are visible during data collection and not present at test time, introducing a train test mismatch. And then lastly, you can only record the reach states rather than recording the actions that are actually commanded to reach those particular states. But we wanted to revisit kinesthetic teaching to see if it's something that might allow us to speed up policies. Specifically, what we decided to try is, instead of using a robot like the PR2, try smaller arms and try using gravity compensation to make it easier to move the robot quickly. To address the fact that human arms are visible, we can apply image masking or in-painting during both training and test time to reduce the train test mismatch. And then lastly, try to use a well-tuned high frequency, specifically 100 Hertz PD controller to be able to effectively match the kind of the reach positions that are recorded in the demonstrations. And then kind of the resulting interface looks something like this. So in some ways not too dissimilar from an Aloha-like setup where there are 2 arms. But in this case, the human operator is actually directly in front, even closer to the robot's own workspace, holds the grippers with some kind of handles on the grippers, and then can directly move the arms, potentially a lot faster than using an Aloha or puppeteering-like system. Now, how does this actually compare to using Aloha? We tested this with 1 expert operator who is on around the paper and 7 novice operators who didn't have much experience with teleoperation systems on a pretty challenging battery insertion task into a remote control. And in red, we're showing the kind of the learning curve of this novice operator on the Aloha system. And in blue, we show the learning curve over 10 trials on the what we call Aloha Lightning system. And what we see is that for novices, they're able to complete tasks 2 to 3 times faster when they're actually holding the grippers in their hands with gravity comp and so forth, compared to using a puppeteering-based setup. And then in these dashed lines at the bottom, we see an expert operator, and we see the expert operator on this kind of kinesthetic teaching system is near human speed at the task, where gray is just using human hands at this kind of battery insertion task. Now, even if we can collect demos quickly, that doesn't mean we can learn effective policies. And so we also use the masking approach to train policies and evaluate them on the robot. And we did this on a few different tasks. So here's kind of a 1x speed video of clearing a tray of objects into a bin, which the robot's able to complete in 7 seconds. Here's the battery insertion task that I mentioned before. The policy is able to complete it in about 6 seconds. Here the robot is kind of singulating a cup. So these are tasks that are really precise, and we really wanted to test the precision because we're not getting the commanded actions in the demonstrations, and this is stress testing the ability to learn from that kind of demonstration data. And then lastly, here's a short scolding task where it's able to fold the shorts starting from a flattened position in 6 seconds. So all things that are quite fast by robot standards. Quantitatively, we also compare this to puppeteering with double the frequency at test time to try to post-hoc speed it up, as well as skipping actions. And we find that we get similar or better success rate with using this kinesthetic teaching teleoperation system. And the policies are 2 to 3 times faster than using puppeteering. So quite promising results. Cool, so that's on the kind of policy speed side. Now, another bottleneck that I mentioned is the scalability of evaluations. And the reason why this is a kind of a bottleneck is that even if you have a single task robot policy, this is already quite time consuming to evaluate because you need to sit down with a real robot and run the robot for multiple trials to get even just a single success rate number. And as our models become increasingly general and ability to do many tasks in many different environments, evaluation increasingly becomes a bottleneck. And one of the things that I found with generalist policies is that you will evaluate them in one environment, and that the performance in that one environment will be completely different than the performance in a different held out environment. And likewise, if we start to see task generalization, we might see that it kind of generalizes really well to one task, but it really kind of generalizes quite poorly to another task. And this means that we need to collect data on lots of different environments and tasks, especially environments and tasks become individual test data points, and it becomes really, really hard to scale the evaluation of these generalist models. So how do we try to address this? I don't have the answer to this. It's really, really hard. But one thing that we've been exploring recently is trying to use generative models to evaluate generalist policies. And specifically, we're aiming to try to develop an action conditioned video generation model where we could potentially run the policy inside that video generation model to test the abilities of the policy. So to try to get this sort of action conditioned video generation model, unfortunately, a lot of the existing models out there, well, most of them are just passive models. They can't condition on actions, and so they aren't kind of immediately useful for evaluating policies. But second, a lot of the action condition ones aren't good enough, aren't accurate enough to really be used to evaluate generalist policies. So what we're going to do is we're going to use the pre-trained stable video diffusion model, and we're going to fine tune it on diverse robot data to try to learn kind of a simulator for this robot. The architecture looks something like this. There's a lot of details here, but I want to highlight a few different things. The first is that this video model is going to be using multi-view images. We're specifically going to be training this on the Droid dataset, and so it has 2 different base camera views and 1 wrist camera view. And we found that including all 3 of these views, especially the wrist camera, was really, really helpful for improving performance in a number of different ways. The second is that we're going to be conditioning on actions, and specifically we're going to be conditioning on actions in a way that's kind of aligned with the current frame prediction to try to make sure that the model is actually paying attention to the current action when predicting the current frame. And then the last thing here is that we're actually going to be using memory in this model as well. So we're going to be having past image frames as input to the model, as well as past proprioceptive input. And we're going to be using cross attention between the past frames and the past proprioceptive input to try to encourage the model a bit to be able to kind of use attention to recall past frames that have a similar arm state. And those frames might be the most useful for making the next prediction. And generally, this sort of memory overall will be really helpful for temporal consistency between future predictions and past frames. Cool. We trained the model on the Droid dataset using both the successful demos and the failed demos. And one thing that I'll highlight is that all of this model is pre-trained except for the action encoder. And this allows us to really benefit from kind of the web pre-training of this video diffusion model. Cool, so that's the model. Now, there's a couple of questions we can ask about this model. First, are the predictions any good? So here are some predictions. The top row is the ground truth. The second row is generations from this video model. It's able to fairly accurately kind of move this bowl. Here's a video that's representative of prior work, and it actually kind of hallucinates a robot arm coming in from the right, which is kind of from the wrong side. And this kind of highlights the importance of having multi-view cameras, because it's actually, from the initial frame, it's really unclear where the robot gripper is. Here's another example where it's able to fairly accurately, but definitely not perfectly, model this kind of pushing this towel. And the prior work, in this case, is better at modeling the arm, but struggles to model the object motion. So the predictions look promising. There's a couple other important questions. The other is, does it react to different actions, passes input? Is it controllable and reacting to actions that are passed? So we took an initial observation and we passed in different actions as input into the model. This is an action sequence that I think is just from the data. And so it's kind of predicting that it's going to pick up the marker. But let's look at some other ones. So here's a prediction of an action sequence that moves the arm in a different way. And one of the things that's cool here is you can see this making use of the other camera views, because this cup here wasn't in the initial frame. And it's able to see that there's a cup there from the base camera and then predict that in the wrist view. Here's another one where it's kind of rotating and also is able to make use of the different views to predict where the cup is in the wrist view. And then this last example is quite nice because we can see that it has good temporal consistency, where halfway through this video, the pen wasn't actually visible in the wrist camera view, but it's able to still accurately model the pen even after that. And so it's making use of the memory and the past image frames. So this controllability looks promising. And so from here, we started to try to use it for evaluation. And what we're going to be doing here is we're going to be taking the Pi-05 model and rolling it out both in the real world and inside the video generation model. And this is going to be for a novel robot setup with novel camera views, a novel environment, and so forth. And so, and basically both the Pi-05 model and the video generation model have to be able to generalize to this completely new setup with these new camera viewpoints, zero shot, in order to be successful. So it's pretty challenging. So here we see a prediction where the policy tries to pick up this blue block. We kind of immediately see a mistake here where kind of our model kind of doesn't get that it misses the first grasp and retries, but generally is able to capture a decent amount of what the policy is trying to do. It at least captures the intent. Here's another example that is kind of promising, but also has some issues in it, where the robot is trying to close the laptop. In real, it kind of makes it more on the second attempt, whereas the predictions showed it more closing it on the first attempt. And I should mention the world model doesn't get the languages input, only the policy gets the languages input. Here's actually one of the really good rollouts where the video generation model is predicting accurately that it's going to fold the towel. And here's another fairly promising example where the policy is going to be wiping from left to right. You can see that in the video in the center view. And the model predicts that decently well with some mistakes at the end. So the model is far from perfect, but we note that it's able to evaluate the intention of, evaluate whether or not it's kind of the policy kind of following the language command or trying to follow the language command at least. And so we're going to be primarily using it to try to evaluate and improve language following. So specifically, we quantitatively measured the correlation between the robot's performance in real and inside the video model. And we compared 3 different policies. We evaluated on a number of different tasks, both in real and inside the model. And first, we see that there's actually a really close correlation between these generated videos and the real world when you're measuring whether the model is attempting to follow the instruction correctly, basically whether it understands the instruction. And then second, when we actually evaluate downstream success rate, we see that the correlation is less reliable for this final success rate as shown here. And so it doesn't seem like these models are quite ready enough to be used as like a true kind of eval simulator for final success rate. Now we've been focusing a lot on the evals, but as one final aside, we also try to use this world model to actually improve the policy on downstream tasks. And specifically to do this, we can collect rollouts. We can actually evaluate like our initial base policy inside the model on OOD instructions. label the ones that are kind of successful or less successful, and then fine tune the policy on just the successful rollouts for that downstream task. So specifically, we're going to be fine tuning the policy on generations from the video model, and no real data will be used to fine tune the policy. And then we can look at a few examples. So the first example is pick up the object on the top left side and place it in the box. These kinds of spatial relations weren't present in the base model's pre-training data, and so it picks up the incorrect object, it picks up the bottom left object. And then after fine-tuning on the synthetic data, the robot is able to correctly follow the instruction and more frequently complete the task successfully. You could also use pick up the larger red block. It doesn't understand things like larger, and so it picks up the smaller one. Whereas here, after fine-tuning on synthetic data, it follows the instruction correctly. And then lastly, fold the towel from left to right. Again, kind of left to right isn't in the base model's pre-training data, but we can then fine-tune it on synthetic data and is able to correctly complete the task. Quantitatively, we also see that on a variety of different OOD language instructions, the robot is able to have a higher success rate after fine-tuning on the data generated by the video model. Cool. So kind of in summary, I think we have promising tools for evaluating these two bottlenecks, specifically the speed of policies and the scalability of evaluations. There's also a number of important challenges that remain with these particular approaches. So with regard to kinesthetic teaching, we use masking of the human hands, and this seemed to work on the tasks that we were looking at, but they may block important task details for certain tasks. And it can also still be tiring even when you have gravity compensation turned on. And then along the front of using generative models, the model isn't quite accurately modeling the physical details, and we see this with a lot of generative models, not just our model. And so I think that thus far, what we've seen is that it can work well for instruction following, but can't work for generally improving the model in other ways. Cool. I like to highlight the students who led this work. Specifically, John led the work on kind of Aloha Lightning, and Yanjing led the work on using generative world models with Lucy. And if there's time, I'd be happy to take a question or two. Thanks.
Justin, we have time for one question.
Go ahead.
So it's been tangential, but I'm curious, there's like all this video data on the world, and there's ways to leverage in the generative model of like kind of simulation. The other is that you can have video-based models, and then you find the policy like base pre-trained model. If you have to choose one, let's say 5 years in the future, which one of these would make the biggest impact to provide?
If I had to choose between what and what, sorry?
Basically, like generative models that can create videos where maybe we can train with them or something like that, versus video-based model where it could be used as like a binder domain like which would be the thing that would be made the biggest impact?
I think it's really hard to say. I mean, with the generative model, you can always generate a bunch of stuff and then train the checkpoint. So maybe that like encapsulates both in some ways, but maybe that's a cop-out answer. Yeah, I think it's really hard to say. I think thus far video generation models have not been accurate enough for a lot of robotics applications, even the really powerful ones. And so like pre-trained checkpoints seem to be really good. I think part of the challenge is we don't have that much robot data that's in these video models typically because there isn't that much robot data, or it's not like we don't have that, like we have some big promising data sets, but we don't have that much compared to all of the other video data. Yeah, I think a lot of work to be done.
All right, everyone, let's take Justin one more time.
So we get set up here where the mic is.
All right, everyone, as Max is setting up here, I'll quickly introduce him. We're very excited to have him here today. Max Simkowitz is an assistant professor of machine learning at CMU. His work studies the theoretical foundations and new methodologies for machine learning problems with an interactive, sequential, or dynamic component. He received his PhD from the University of California, Berkeley, under Ben Recht and Michael Jordan, and he completed his postdoctoral research under Russ Padrake in the Robot Locomotion Group at MIT. His work has been recognized with numerous Best Paper Awards, too many to enumerate here today. And so without further ado, we'll let you get started with your talk.
Thank
Really
you.
happy to have
Thanks everyone for having me. Thank you, Rohan, for getting my last name right. That's incredibly impressive. Yeah, so this talk is going to maybe be a little bit different than other talks in the workshop and potentially other talks at the conference, in that it's going to try to bring a theoretical perspective on some of the things that we do in robot learning. So I'll just kind of get started. So I think kind of the theme of the workshop, and I think it's pretty difficult to disagree with this, is that modern robot learning is all about the data, right? So kind of 2, 3 years ago, 4 years ago, we started to see a bunch of different work. We try to make it easier to collect more high quality data across multiple tasks to enable kind of generalist policies. And certainly we've also seen these techniques becoming a really popular industry with recent startups, using these things to kind of have really impressive demonstrations. But at the same time, I think it's also rather uncontroversial to say that this kind of uptick in the success of robot policies kind of coincided with the discovery of a couple kind of quirky design methodologies that also seem to make things work a lot better, right? So like taking off with generative policy parameterizations like diffusion models and flow models, the use of non-learned control stacks, right? So we like to think we're doing end-to-end learning, but we pay a lot for our robots that have really carefully tuned hardware. And a bunch of other kind of essential, but still very somewhat mysterious design decisions. And in fact, today I'm just going to talk about one, but try to draw some broader lessons. So that design decision is action chunking. A little bit just kind of philosophically about why I'm talking about this. So kind of the claim that we're going to try to establish via action chunking is that modern robot learning and kind of many of the design decisions that we take in robot learning can really be thought about taking our control system between the robot and the environment and reparameterizing it in such a way that we can learn better. And it's kind of under the conditions of this reparameterization that we're now in a regime where things like the bitter lesson can take effect and where we can scale. And why bother understanding what works? I think this is a question that I personally wrestled with a lot. And I think as impressive as modern robot learning is, we still have major fundamental challenges ranging from dexterity to zero-shot dynamic transfer to reliability. And I really see this as just kind of at the beginning of kind of the road to generalist robots that can do all the little things we want them to do. And hopefully by understanding what works now, we'll have some more insights when we kind of face the more difficult challenges in the years to come. So just a refresher on what is action chunking. I think much of the audience might be familiar with this practice, but essentially what we do is we take some high dimensional observations that a robot sees, maybe a sequence of these observations. And then what we use these to do is to produce not a single action, but rather a chunk or sequence of actions, which we execute typically in open loop, where we execute some subset of these in open loop. And then finally, we deploy this, our robot sees the next states, sees the next sequences of observations, and we sort of go and we continue in this fashion. So there have been a number of hypotheses as to why action chunking may be beneficial. So for one, you might think that this improves representation learning, right? You're predicting an entire trajectory with kind of more meaningful information rather than just sort of individual actions at a time. You might think that using action chunking, it introduces non-Markovianity into your dynamics because you're sort of correlating your current actions with past actions. And this might be really useful if, for example, you have partial observability of the system. And lastly, there are lots of nice parallels between predicting long sequences of actions and preceding horizon control, right? So making a longer term plan and only enacting a little bit of it. But in fact, what we're going to show later in this talk is that there's an experimental setup which ablates these things away and shows that even though certainly these could be benefits, even in regimes where none of these hold, we still see benefits to action chunking, right? So even the benefits of action chunking persist even when we don't really persist if we only predict one action. So it can't simply be about representation learning about the prediction objective. The benefits persist in state-based control with full observability. So it can't purely be about resolving non-Markovianity. And finally, if you execute an entire action chunk, you can still see tremendous benefits. So it can't still be just about receding horizon. So we'll try to dig into what's going on. So the complementary perspective that I'm going to bring is action chunking is actually should be understood as a control theoretic tool. Benefits are control theoretic in nature. And they're witnessed even in the simple setting of state-based deterministic policies, which is not the setting in which action chunking was first proposed. So let me kind of just describe where I'm coming from. So we can think of robot learning as a control problem. This should be relatively uncontroversial, right? So we take actions, the actions proceed through our dynamics. The dynamics affect state, which typically we don't get to fully see. We only see some observation, but we plug that observation back into our policy, taking new actions and so on and so forth. So that's not so interesting. But I mean, maybe what distinguishes control from a general MDP, from general decision-making like you might see in RL, is the presence of decision-making in the presence of stability, right? So as control theorists, kind of the central object that they consider is this notion of stability, which roughly refers to the sensitivity of your dynamical system to perturbations of its inputs, right? So kind of the two canonical cases you can think of stability, I'm not going to give mathematical definitions because it's a short talk, but a system is stable, think about a regular pendulum, right? It's upside down, and so when you perturb it, it's going to sort of relax into its equilibrium. On the other hand, if we have a pendulum on its other side, right, any small perturbation can knock it over. It's highly sensitive to these perturbations. So there are a number of scenarios of what we call incremental stability, which focuses on the sensitivity of inputs. So where we can think about some malicious adversary that's going in and perturbing inputs to our system. We'll say a system is open loop stable if just perturbing the inputs doesn't cause the system to change too much. This is typically the case that we see in modern robot learning with the kind of pushing, pick and place tasks, kind of pushing objects. Systems are relatively stable. There's also closed loop stability. So this is what happens when we have a policy running in feedback with our environment. And it says that perturbations of that policy also won't cause things to go too far awry. But the last scenario that will also arise in this talk is the notion of closed loop instability, where if we make perturbations to our policy, this is going to cause feedback with our system that will push things further and further off course as time continues, right? And this is a situation that we want to avoid. And I should also mention that there is open loop instability, but in modern robot learning, this is something that we're not really tackling quite just at least in manipulation. So why does stability matter in robot learning? Well, we can think about behavior cloning, right? So imitating an expert demonstration. So imagine this is a trajectory of an expert in cartoon form, and we'll assume that the expert is always closed loop stable, meaning your teleoperator knows if you make a little mistake how to get back on course. So what are we doing in behavior cloning? What we're really doing is just learning from the states in the expert distribution. So we're trying to make predictions of actions that, when anchored at the states in our data, are close to what the expert would do, right? But of course, that's not what actually happens when we deploy our policy. When we deploy it, we take actions in sequence. And these errors that they make can compound over time, leading to further drift away from the distribution that you want to imitate, right? So we call this the compounding error problem. You can readily see that if your learned policy is closed loop unstable, you're not going to be in for a good time, because small errors that you make are going to be transferred and are going to kind of grow considerably larger. So what can we say theoretically about this? We can actually create the following mathematical construction. So fix any target error scaling law that you would like, say polynomial inverse of n. And what we can show is that there exists open loop stable imitation learning problems, where actually both the dynamics are stable and your expert demonstrator are closed loop stable. But you run into the following issue. Your validation loss in your behavior cloning problem of Bayesian scaling law goes down like n to the minus alpha. But if you try to deploy your learned policy, this is going to blow up by a factor of 2 to the horizon. So it's going to be exponentially worse, right? And this is somewhat surprising, because this is happening even if our dynamics are nice, and also even if our expert demonstrator is also really well behaved. And really, this is an issue that doesn't depend on behavior cloning. It actually happens for any imitation learning algorithm. It's much more tied to the policy parameterization. So this is policies that are not doing action chunking, rather than the algorithm. So if you did inverse reinforcement learning, if you did Q learning, you're not going to break this negative result. So why does this happen? Essentially, what we show is that there exists a setting where no single policy is both consistent with the expert data, but can stabilize all possible dynamics outside of the distribution of the expert data. So imagine that your expert data manifold is kind of lying on the y-axis, it's in the blue. And you can imagine trying to design a policy that agrees with the expert, but when you go off course, it would still stabilize the dynamics if the dynamics were given by this gray function, f1. But it turns out, unfortunately, that there will be some other dynamical system, which you don't know, you haven't seen data there. And if that were the two dynamics, you would unfortunately have to destabilize it. So you really cause this kind of catch-22 where you're not able to stabilize one or the other. And you can check out the paper to see what the mathematical construction looks like. So a couple issues or notes. One, if you had good non-expert data, that would fix this, right? This is the data curation workshop. So I think this really also says that there are other ways to do things in terms of great data curation. But of course, we can never collect all the possible failure mistakes in the world. We did at least like policies that have some inbuilt robustness. I think the second note is that this is very different from other settings where we use pure supervised learning for pre-training. So for example, in discrete settings like LLMs, compounding error is only at linear in the horizon, rather than being exponentially large, right? So this is something that's very unique about learning in the continuous physical world. Cool. Maybe one last other point of contrast. So in traditional control, for example, in the 70s, when people were trying to fly airplanes in like the Cold War, the real challenge was that your dynamical system itself was really nasty. You had to stabilize an airplane that had to be incredibly agile to do these crazy maneuvers. In modern robot learning, at least for the task we're thinking about, the dynamics are actually quite nice. What's really hard is that the black box policy itself is the thing that has to be stabilized, both because the neural network might be ill-behaved, but also because it has to be queried in OOD situations. And so I think reframing state stability from something that's about hard dynamics to difficult learning conditions, I think is something that's going to be quite novel that we have to encounter in modern robot learning. Okay, so where does action chunking come in? Remember, in action chunking, what we're doing is we're predicting sequences of actions rather than actions in open loop. So actually, we're able to show something that's quite remarkable, that if you just do action chunking with a fixed but sufficiently long length, you break this exponential compounding error issue. So rather than having 2 to the h multiply your scaling law is multiplied by a fixed constant. Essentially, action chunking is avoiding compounding error. And really what this bound does is it saturates at a fixed chunking size, right? So it doesn't say that you're, it's not like just saying, oh, I'm just shortening my horizon by some effective amount. It's really saying that I'm changing the fundamental dynamics of my control system. And we can actually simulate this on I'll get to more interesting experiments later, but we can simulate this on our toy construction that witnesses this mathematical counterexample. And you can show that as you use smaller and smaller action chunks, your compounding error is less and less drastic, or larger action chunks, your compounding error is less drastic. So why does this happen? Really what's going on is that the rare policy updates are leveraging the open loop stability of the dynamics. So even though you could go compound and go way out of distribution, if you use the fact that the dynamics are stable and aren't too sensitive to perturbations, you kind of allow the dynamics to carry you back to where you would have gone otherwise. And we can make this precise in mathematical sense, but it's a little hard to do for a short talk. So maybe one way to think about this, way I think about this, is action chunking is actually creating a different dynamical system. So now your dynamical system doesn't take in one action, but it takes in a sequence of actions. And it turns out that in this parameterization, the imitation learning problem enforces closed loop stability of the learn policy, allowing you to avoid exponential compounding error. So how do we test this hypothesis? What we do is we set up a situation where we can ablate away the other possible explanations for action chunking. So we look at a state-based regression policy trained from a deterministic expert. What we do is you train a flow policy and you generate data by flowing it from zero and do some filtering to make sure you have good demonstrations. And so what we can show from here is that there are certainly gaps. So in the different colors, what we're predicting are the different action chunks that are done in training. And on this axis, we're looking at the evaluation rate. And certainly it's the case that the amount of actions that you predict does affect the performance, but you can see that the dominant trend is really the length of the actions that you execute, right? Rather than the actions that you train on, which give credence to this hypothesis that really it's about executing long actions, chunks, and reparameterizing the dynamics that drives the effect of action chunking. So this is also very consistent with why we find that we use end effector control parameterizations in robot learning, right? Remember, our core assumption for why action chunking works is that the dynamics are stable. And it turns out that end effector control precisely puts us into this regime, right? So when you make position commands, what it's essentially doing is it's just tracking the positions that you desire. And so if you made a little mistake, well, your position control can make up a large amount of the difference, right? So this what this really suggests is that sort of action chunking and end effector control have this unique synergy, which is avoiding this exponential compounding error and really making our scaling laws behave a lot more nicely. Cool. So again, of course, theory doesn't tell you everything. There are lots of banal hypotheses for why action chunking work that are also valid. So for example, when we collect expert demonstration data, oftentimes it has a lot of pauses. If we don't do any action chunking, we can just get stuck in an infinite loop. So I think it's important to keep in mind, this is not sort of a totalizing explanation, but I think the control theoretic explanation still does help. And I think the previous experiments we showed sort of provide evidence as to this effect. So what happens with unstable dynamics? I'll mention this very briefly. It turns out that with unstable dynamics, right? So imagine you want a robot basketball player or something crazy. You're not going to really, your imitation learning alone is really not going to be able to cut it, right? So what we can show is that in this case, there's no algorithm, right? Without collecting more non-expert data that's able to beat this 2 to the h compounding error, right? So our scaling law is kind of putting us into this valuation. And really what this says is that when we're doing unstable robotics, as we move towards more dexterous, more difficult tasks, we're going to need to increase the coverage towards non-expert demonstrations as a form of learning, or alternatively use interaction reinforcement learning as a way to train these agents. So maybe just let me recap and then kind of go from here. So my kind of claim that we try to show in this talk is that modern robot learning, the design decisions that seem mysterious, are really about reparameterizing the closed loop dynamics between the robotic agent and the learner more broadly. And that essentially what's going on is it's not that the dynamics are super hard, but rather that our policy, stabilizing this learned black box policy OOD is the fundamental challenge that we have to circumvent. So maybe what I'm going to ask is, can this perspective be more useful beyond just action chunking and give us insights into some other design decisions? Right. So actually in some soon to be released work, we're actually going to try to answer the question, why do we use flow and diffusion policies? And I can't go into it here, but the big TLDR is that generative controllers are really about regularizing OOD behavior. If their fundamental effect is this, in fact, multimodality is quite limited. It doesn't show up in almost any of the popular robot learning benchmarks. It's really about regularizing OOD behavior. And then in some work I'm incredibly excited about, but unfortunately can't share too much about, it's still in progress. We're able to show that changing the optimizer itself for how you train, so it's changing from Atom to some other kind of optimizer, is able to prevent sort of distribution shift within the layers of the network itself, improving imitation learning performance tremendously, right? So again, you see the theme is that sort of all these design decisions really come to regulating OOD behavior, encouraging various forms of stability and reducing compounding error. And of course, in addition to all these, still there remains the kind of the big question, how we use these insights for the data. I won't have much to say about them today, but probably the most important part of all the robot learning research we do is the students. So I want to thank Thomas Zhang and Daniel Frommer for leading this work and their advisors, Nick Montney and Ali at MIT. Thank you.
You can take a couple questions.
Yes.
So these results change the action space. Say, for example, it's in velocity space.
Currently not. I would imagine you can reparameterize them so if they work in velocity space, it would work as well. Right. Yes.
We cover utilization variables today. Mention chunking in general is more smoothly, not actually. Have you had a chance to look?
So I in my experience, at least in many computing applications, it works best when you do actually. At least one course has. I mean, I've seen in many cases. Yeah, so these tools on this, a lot of them, right? We get words back.
So in order to successfully get to CoRL, they had to so that's yes.
No, I think the question is if you're doing this for on-policy or else. The on-policy reinforcement learning, at least in my medicine group. So I think at least in on-policy reinforcement learning, no additional modifications have to be made. If you want to use off-policy reinforcement learning, you need a key function. And when you have a key function, you have to attend to longer sequences of action. So typically this requires some architectural design decisions to be made, but it's really about the policy representation. It's not really the action. Actually, what I would say is probably in RL, you need action chunking less, or ideally you should need it less because you can overcome the instability through online interaction. Yeah. Yeah.
All right,
Cool.
everyone, let's take that one more time. And with that, we're going to do a break. We'll be back at 2 p.m. for tutorial on data mixing, and then 3:40 for the panel session.
Yeah, we do, yeah, okay, I think I had it back. No, but it'd be great to have it, but it's okay. Let me see how it's about 50 minutes. Yeah, that's basically. But yeah, no worries, no worries. Yeah, no, I bet, okay, yeah. Okay, but I work with it, came out with lots of attendance. Which then Max, yeah, Max does great work. I mean, that's not easy stuff. I mean, that's a quite good piece, and then actually, but it was very good. Yeah. Okay, we'll see you. Yeah, we'll get dinner or something. See you. Yes. Okay, everyone, we're gonna get started. We're gonna have a tutorial on data mixing. So Mei Chen is a PhD candidate in computer science at Stanford University. She's advised by Professor Christopher Wray. Her research focuses on advancing the fundamentals of artificial intelligence through data-centric approaches, particularly in training data curation, where she has developed techniques for data mixing, curriculum learning, and weak supervision. Her work has been recognized with the Best Student Paper Award runner-up at UAI 2022, a Best Paper Award at AAAI 2022, and spotlights at iClear and Europe's 2023. Mei is currently a research intern at AI2, driving the data mixing efforts for OLMO3, their next generation open source large language models. Before Mei gets started, I just want to say it's super exciting that she's here with us, because it's often very difficult to get a non-roboticist to show up at workshops, and we think there are a lot of interesting insights in large-scale training of language models that apply to large-scale training of robotics models these days. With that, Mei.
Thank you, Chris, for the lovely introduction. It's great to be here. So my name is Mei Yi, and I'll be presenting a tutorial on data mixing, which is a powerful tool in curating training data sets. So in the LLM world, it is increasingly accepted that good data is critical to the performance of models. So the latest models are trained on over 30 trillion tokens, and every organization that is training an LLM basically has an entire team working on making sure that the data is as good as it can be. Recent model reports like for Llama 3 also repeatedly highlight the investment made into constructing data sets. So I thought it might be helpful to first look back at how we got here. So how did the field of AI get to this point of recognizing the role of data? So you can think of two core parts of an AI system, the training data and the model. And so for many years, people had focused on model-centric AI. You use a well-known training data set like ImageNet or CFAR, and you would focus on improving the model architecture and training procedure. Then starting in around the late 2010s and early 2020s, people started thinking a lot about data-centric AI, and they realized that a lot of performance gains were in the data. So you could just use a fairly standard model architecture and training procedure and really just focus on improving that data. And here was when people started thinking about things like automated data cleaning, data augmentations, and a lot of techniques. So while this data-centric AI idea was growing largely in enterprise AI, the LLM story was a little bit different. So around the same time, the first modern language models started coming online, and each of them had more and more parameters, as shown in the figure on the left here. And scaling laws research really suggested that all you needed for better performance was more parameters and more data. So as time went on, people started training on larger and predictably messier data sources. So for instance, BERT, which was from 2018, was trained on books and Wikipedia, while GPT-2 was trained on Reddit, and GPT-3 was trained on a mix that included Common Crawl, which is massive open web scrape containing over billions of web pages of data with highly variable quality. So of course, during this time, there was definitely still a hunch that quality and other properties of data still played a role, but a lot of the previous data-centric work was at a smaller scale, and there weren't many studies that demonstrated if better data could shift how to design these large language models. In around 2022, however, we started seeing these first large-scale studies that showed that quantity was not everything. So several papers started showing that smaller, smartly pruned data sets could actually be quite advantageous, as suggested in the plots here. So from here on out, people started more widely accepting the fact that having good LLM training data was important as having a lot of data. So lastly, before I go into more technical components of the tutorial, I wanted to share a bit about my background. So I'm not a roboticist, but I'm always curious about the area. I work a lot on LLM data, and I partnered with various organizations such as Snorkel AI, Together AI, and the Allen Institute for AI. And I've been involved in the creation of several language models and their large-scale training data sets. So I really hope that this tutorial can encourage our two fields to have more conversation around developing data-centric approaches. So the rest of the tutorial is shown here. First, I will discuss the general LLM data development pipeline, breaking it down into what are properties of good data and what are the mechanisms for creating a good data set. Then I'll go into my area, which is data mixing. Broadly speaking, data mixing is a mechanism for combining data sets. So I'll go over the basics of why we need this and what it is. And the technical meat of this part would be on something called mixing laws, what I believe is a fundamental unlock that really elucidates and organizes this research space. Then I'll discuss several methods that are built on mixing laws and the implications of these mixing laws. So there are many things that can define good data for LLMs, but here I've broadly categorized them into 3 buckets. Quantity, which is just the number of tokens, quality, which you can think of as sample level properties, and composition, which are dataset level or group level properties. So first, even though I said earlier that quantity isn't everything, it's still incredibly important. So you can see that with the growing trend that even the latest LLMs continue to be trained on more and more data. So for instance, you can see for the Llama family, it's been consistently increasing up to 30 trillion tokens. Second is quality. So you can think of these as individual characteristics in these text samples. So for instance, here I'm showing you some samples from a data set called FineWeb EDU. For the EDU part, basically what people did was the Hugging Face people trained a model to score how educational each sample was, and they only kept the samples that had a score of higher than 3 out of 5. So in the red and the blue here, you can see that you want to keep these samples that are high quality, like the definition of a vaccine here, and you want to remove these low quality samples, like the one, the red one above, like it doesn't really say much. And then finally, we should care about the composition of the training data set. So when training a model, you usually want it to do many things well. You may want it to summarize long documents, write code, talk with us, do all these things. And so naturally, the training data should be composed of data sets that consist of these long documents, this code, this dialogue, and all these things. So we need this notion of kind of like matching between data sets and the desired capabilities. So we've discussed these 3 nice properties that we want, and now how do we go about achieving those? Here I've abstracted data development into 3 mechanisms: acquiring data, which increases quantity, transforming data, which improves quality, and mixing data, which helps control the data set composition. These 3 mechanisms are typically chained together in the following way to get a final data set. So first, you would acquire various sources of data. For example, one practitioner is responsible for curating the GitHub data, while the other one curates the Wikipedia data. And then each of these data pools are transformed, and finally, they are combined via mixing to produce the final training data set. So next, I'll provide an overview of each of these mechanisms and the techniques that are being used there. All right, so first is data acquisition. You can think of this as really just going from no data to some data. And nowadays, there's so many ways to do this for LLMs. You can crawl for the data yourself, or if you want something simpler, you can download an existing data set. You can also synthetically generate the data, which is pretty cool. This was an idea that kind of grew from the Microsoft Phi models, and one of their papers called Textbooks Are All You Need. And more recently, this has been done by the Hugging Face team with this data set called Cosmopedia. And basically what this does is you have some seed samples that are true data, and you get an LLM to create new samples based on those. All right, next is data transformation, which can be categorized into data filtering and data rewriting. So first, data filtering is a massive area, and I could talk about this for a lot more. But there's a ton of things you want to filter for, basically. And they kind of go from coarse to fine. So at the coarsest level, people will filter for things like punctuation, certain keywords, URLs. These are just like heuristics that the practitioner knows, like this URL doesn't have anything of value, it's just not included. Then going a step farther, it's also important to deduplicate. So the idea here is that you don't want a sample that appears over 1,000 times in your data set, but when you're scraping the web, a lot of content is repeated on different pages. Finally, moving towards the more advanced types of filtering, you can use a model to determine if you want to keep or discard a sample. So for instance, what I mentioned with the Fine Web EDU samples earlier. And also you can filter not only for quality, but you should also filter for things like safety, sensitive information, licensing, and so on. The second category we have here is rewriting, which I would say is a somewhat newer type of data transformation that a lot of people are starting to look into. So the main idea here is to transform a text document into a particular format. For instance, you take some web page and you create question answer style writing, or you rewrite it as like a Wikipedia style page. And that kind of improves the quality and aligns the data more with how people use these models. And then the last mechanism is mixing. So this one focuses on taking M data domains and combining them to create a final data set that leads to a range of good model capabilities. And this, of course, brings us to the next part of this tutorial. So now we're going to go over a more detailed look at data mixing. So as I mentioned before, mixing is the procedure of figuring out what ratio you need to combine your data sets, such as your model exhibits all these capabilities. More formally, we have a set of M data domains, and we want to determine in what ratios P should we sample the domains to produce a strong model. Before we start discussing how to mix, it's actually important to also step back and ask, why do we even need to mix? What does it enable? And the reality is that modern LLMs are not trained on a single data set. They're almost always trained on a collection of different sources, simply because there are so many places to acquire data from, and there are many people curating these data sets at the same time. So in some sense, mixing is inevitable. And even if you said that you didn't want to do mixing and you just concatenated all your data sets together, you effectively are still inducing a mix, like a ratio over your data sets. So it's natural that we want to get the most performance out of a procedure that is inevitable in the data development pipeline. Then beyond being kind of inevitable in practice, mixing is uniquely useful in that it allows us to control the training distribution using the mixing ratios as a low dimensional knob. So adjusting this knob helps us smartly navigate and optimize trade-off space among various model capabilities. And we indeed do see that mixing, when done well, can improve performance dramatically across model capabilities. So in the figure shown here, the green line indicates a good mix from one of my papers, and you can see that on all 9 tasks, it obtains better performance than the other 2 mixes. So this shows that mixing can really make a difference, and therefore it needs to be done with thought. So a very straightforward way of getting a good mix is to simply apply a naive search-based method. This would mean that you start with some mix, you train a model using it, you see how it is, and then you continue to manually adjust the weights based on these vibes, as they say. And the problem with this search approach is that it's quite costly, and it requires you to train a bunch of models on different candidate mixes. However, I will say it is a tried and true technique. It's been used across different models and domains over the years. So next, I'll go over the 2 settings for mixing and their formal problem setups. In data mixing, we consider what are called static and dynamic settings. So in the static setting, we determine a mix P, and we train the model, the entire model on it. So we just fix P and we train for, then we just hit run. In the dynamic setting, we adjust the mix throughout training such that the model is trained on the initial mix for some number of steps, then another mix for some more steps, and so on. And currently, I'd say that there's not really a right answer for whether static or dynamic mixing is better to do. It really boils down to what are the pros and cons for the practitioner. So for static mixing, the main advantages are that it's quite simple and reusable. So you prepare your training data set according to the mix, and you can hit run and you can do everything else normally. These mixes can also be reused and passed down as good references for future models. So if I see a paper that reports, you should have 30% code, then I know that, for my next model, I should use a similar amount. The one drawback, however, for static mixing is that it could be possible that it doesn't fully take advantage of how the model changes as it's trained. So there's a risk that a static mix becomes stale as the model continues to train, and then it'll be suboptimal. So this is where dynamic mixing shines. It allows you to adapt your mix as the model learns. And this can be quite beneficial in some cases. So for instance, in some of my previous work, I showed that it's helpful for the model to learn 1-digit addition before 2-digit addition. And so a dynamic mix could take advantage of cases like this, where you start with learning more of 1-digit addition, and then as that skill becomes mastered, you would adjust your mix to learn 2-digit addition. The problem is that there are a few drawbacks of dynamic mixing, which is that it's not very straightforward to implement. It's not compatible with a lot of standard trainers. And the dynamic mixes are specific to the model, which makes it difficult to reuse and pass down as folk knowledge. So we've established that both of these settings are valid and worth studying. So now I'll give the formal problem definition for the static mixing problem. So we're given M training domains D1 through DM, and we want to train an LLM on N tokens. The data mix P is a probability vector over the M domains, and the final mixed training data set is created by sampling N times P of I tokens for each domain DI. We then denote LM of P as a model trained according to data mix P on the domains, and then we evaluate this trained model on N validation data sets, where F of I of LMP denotes the validation loss on dataset I. So for these validation data sets, you can think of them as either held out splits of the training domains, which means that N equals M, and we're just evaluating in-domain performance, or these validation tasks can also be out of domain, such as downstream tasks. Now, the static data mixing problem is to find the data mix P that minimizes the average validation loss over all of these validation data sets. And the main goal is if we can compute this optimal P in a way that is more efficient than just a brute force search. Next, for the dynamic mixing setting, we split training into T stages. And so rather than having the mix P be held constant throughout training, we consider a mix that can change at every stage. So we train on data sampled according to P1 for the first N over T steps. We train according to P2 for the next N over T steps, and so on. This makes the dynamic data mixing problem much harder. We want to learn the optimal mixture trajectory, the sequence of P1 through PT, and we want to compute this trajectory efficiently. So as you can imagine, these are pretty hard problems because the search space over mixes can just be very large. And over the past 2 years, there have been a lot of data mixing methods proposed, and they're doing all sorts of things, including some of my earlier work, like some are using bandits, some are using portfolio optimization, and every single one of them works quite well on the data sets they evaluate on, but it isn't really clear which one is best and what they're really doing under the hood. And so sometime around last year, amid all these methods, several papers, including one of mine, started to chip away at this fundamental development called mixing laws. The key insight here is sort of a scientific one, which is that there is a structured relationship between the data mix P and the performance of a model trained on P. And the significance and why this was so exciting to me is that if there's a structured relationship between the mix and the performance, we should really be thinking about how to understand this relationship and use this relationship to guide our data mixing. And this was a fundamental shift for me in how to really view this space. And it moves the question away from let's just design a method that obtains a good mix to this question of understanding and exploiting this scientific property of how models learn from data. So this particular structured relationship is shown here. The relationship between the mix and the performance of a model trained according to this mix follows quite a simple parametric form. And the key property to note here is that F, the performance, is expressed using a linear function A transpose P, on top of which other monotonic transformations are applied. And so this structure and this linearity is quite interesting. So what this means is first that small changes in P result in small changes in model performance, which makes sense naturally. And second, this linearity is super interesting. It means that each domain additively contributes a term Aij to the performance. And so this Aij can be thought of as a true score for how much domain J impacts validation data set I. So I've shown the general format of this structured relationship expressed as this roughly linear mixing law. And so now I'm going to go into two methods, one static and one dynamic, that focus on first understanding this mixing law and then utilizing it in their algorithm. So first is a paper called Data Mixing Laws, which I believe was the first to coin this term and come up with this structure. And this paper focused on the static mixing setting. In particular, they showed that the validation loss could be approximated as an exponential and linear function on the data mix. And in both their experiments and my work, it's been pretty rigorously validated that this mixing law holds quite well in practice. So in the figure here, you can, what we're doing is we're mixing over just two domains, archive and stack exchange. And on the x-axis here, we're changing the proportion of the domains, and on the y, we're observing the validation loss. And you can see that the performance predicted using the mixing law very closely aligns with the true performance. In addition, the R-squared value of the static mixing law on Slim Pajama, which is a popular pre-training data set, is quite high. So once this paper established the validity of this static mixing law, they focused on how to use this. So their approach could be broken down into three stages, what I call explore, fit, and optimize. So explore and fit involve learning the mixing law, and optimize involves exploiting it. So first, in the exploration stage, many small language models are trained on a bunch of different mixes, and we record the validation losses corresponding to each mix. This creates a set of inputs P and outputs Y, and in this fitting stage, we use this set to estimate the parameters of the mixing law. Once this mixing law is fit, this essentially gives us a surrogate model that can predict the performance of any mix we pass into it. And so in the third stage, optimization, we use the mixing law as a substitute for the true relationship F, and we can efficiently solve this optimization problem using standard solvers. This method, introduced in data mixing laws, was shown to improve performance. So as you can see in the figure here from their paper, the mix they computed was able to be 1.48 times more data efficient than just random sampling of the data. Next, I'll discuss one of my works called Aioli, which discovers a dynamic mixing law and utilizes it in a mixing algorithm. In particular, we constructed a time-dependent mixing law where the validation loss at stage t+1 is equal to the validation loss at stage t minus some linear function of the data mix at stage t. So intuitively, this shows that the marginal performance improvement at each stage is linear in just the current data mix. So in the figure here, you can see that this dynamic mixing law also fits the true performance quite well, and the R squared on swim pajama is quite high. So now that we've established the validity of the dynamic mixing law, we want to figure out how to exploit it to create a better mix. The simple solution proposed in Aeoli was to split each stage into an exploration and an exploitation phase, as shown by the blue lines and the orange lines. So in the exploration phase, a procedure very similar to the static case is done, but sequentially. So we sequentially train our model on a bunch of different mixes and record the change in validation loss each time. And this creates a set of inputs P and outputs Y, and we can use this set to learn the parameters of the dynamic mixing law. Finally, in the optimization stage, we use this dynamic mixing law as a surrogate model in place of the true F, and we update our data mix accordingly. So we'll use this data mix that we computed for the remainder of this stage. And once we move to the next stage, we will repeat this entire procedure of exploring, fit, and optimize. Our method Aeoli demonstrated clear performance improvements. So as shown in this figure, we compared Aeoli's dynamic mixing approach with data mixing law's static mix. So we considered 5 different data domain settings. And across all these settings, Aeoli consistently offered improvements. And so the key takeaway here is that there is value in dynamic mixing over static mixing. Now I'll move on to why I am very excited by this way of thinking about data in terms of these mixing laws. So in particular, these mixing laws are an incredibly useful tool in understanding both existing mixing methods and understanding our data more. So as you may have noticed in describing the static mixing laws in Aeoli, both of them followed this procedure of explore, fit, and optimize. And it turns out that many mixing methods also follow this approach. However, the key difference is that a lot of existing methods do not explicitly fit a mixing law, yet these approaches do make some implicit assumptions on the relationship between the mix and performance. So in fact, in the Aeoli paper, we showed that a lot of existing methods assume the same dynamic mixing law, but the key difference was rather than fitting the parameters from exploration, they hard-coded them as functions of losses and gradients, as shown in the table here. So you can see that the A parameter of the dynamic mixing law varied significantly across methods. So for instance, do-re-mi, one of the first data mixing methods, can be described as using a diagonal A matrix, while another approach called Doge constructs A based on gradient dot products. And the really neat thing is that the performance of all these methods is closely tied with how accurate their implicit mixing law is. So we found that when these hard-coded parameters were really far off from the fitted parameters, this also correlated with cases where the corresponding method performed poorly. So you can see in the figure here, the x-axis is the similarity between hard-coded and true mixing parameters, and the y is performance improvement. And you can kind of see that there's 2 regimes where the hard-coded values are quite off from the mixing parameters and performance is bad, and cases where the hard-coded parameters are quite close to the true mixing parameters and performance is good. So in short, the mixing law provided us with a tool to really understand the consistency and the robustness of a wide variety of existing methods. Finally, I'd like to talk about how mixing laws can help us understand how models learn from data. And I think this is the really cool part that has so much potential and future directions. So recall that this is the mixing law form we have discussed, and we can interpret this as each domain contributes this Aij score for how much domain J impacts validation dataset I. So the big question one may wonder is, what does this A matrix across domains and validation data sets look like? And we would like to know this because you can imagine that there's a sort of like trivial A that is really sparse. For instance, every domain only influences the performance of itself, and if A didn't change at all over time. So there's this sort of like, maybe the true A matrix is a very simple structure, and life is easy and data is independent. But we actually find quite the opposite. So first, we find that this A matrix has quite some asymmetries. So it's rarely the case that one domain only influences one task. And instead, we can have many similar domains interacting with each other and similar validation data sets as well. So on the left here is a figure from the data mixing laws paper that shows that there are off-diagonal interactions among different domains. On the right here is an unreleased figure from some work of mine that should be coming out soon, where we looked at a set of domains that corresponds to topics on the web, and our validation data sets are downstream tasks. So I'd like to kind of look at a few examples of rows in this matrix. So in this figure, we can see that there are some tasks that are only influenced by one domain mainly. So for instance, MedMCQA, which is a medical health task, is most influenced by health data, which makes sense. But it's pretty cool that this is being backed out of this, this sort of mixing law experiment. However, there are other validation tasks that are influenced by multiple domains. For instance, this humanities task, MMLU Humanities, is influenced by crime and law, history and geography, politics and religion, which makes sense intuitively. Similarly, we can see that there are some domains that only impact one validation task. For instance, crime and law really only impacts the humanities task. But on the other hand, we also see that there are some domains that can impact multiple tasks. For instance, there's this science, math, and technology domain, and it affects tasks ranging from ARC Challenge to Jeopardy, algebra, and so on. Finally, as a fun tidbit, these A matrices really can offer some interpretability as well and confirm that models are behaving as expected. So as an example, I've boxed two entries of the matrix here where we can see that food and dining and home and hobbies really influences this task called PICA. So I was really curious, and so I started digging more into how PICA was collected and what it is. So PICA includes questions around physical common sense reasoning, for instance, how to apply eyeshadow without a brush or how to bake a cake. And it turns out that PICA was constructed by scraping from this website called instructables.com, which in fact contains a lot of cooking recipes and home improvement articles. So now it makes sense that PICA is very influenced by food and dining and home and hobbies. So this is really cool because by looking at this learned A matrix, you can better understand what's in your data. So for instance, if I saw that science, math, and technology was not actually influencing all these science and math tasks, I would get suspicious, and I could use this A matrix as a tool to check if my data was collected correctly. Second, we find that the A matrix can change over time. That means that the relative influences of domains can evolve. So in the Aoli paper, we looked at training and evaluating on GitHub and C4 domains, where C4 is a clean version of the Common Crawl web domain. And we saw that the A matrix changed dramatically from step 2000 to step 4000. So in particular, at step 2000, you can see that GitHub's influence on GitHub is 0.63, and C4's influence on C4 is 0.37. So there's quite an asymmetry in what data sets are useful in this earlier stage of training. But once we go to step 4000, things start equalizing a bit. So both GitHub and C4 have influences around 0.48 on themselves. And so this kind of shows that as the model is trained, the relative importance of data is also changing. So to wrap things up, today we talked about the data development pipeline, which can be broken down into some rough stages like data acquisition, data transformation, and mixing, which improve quantity, quality, and composition. We then went into detail about how mixing is an inevitable step in data development and is used to create training data sets that aim to optimize a wide variety of model capabilities. And in the mixing literature, a key development that I'm very excited about is the fact that at pre-training, performance has this really nice, roughly linear structure in the data mix. And this suggests that mixing methods should be designed to exploit this structure to produce better mixes more efficiently. Finally, there's a few directions that I've been quite excited by. So first, a domain can really be any group of data. Typically, people think of domains as data sources, so think of things like comment, crawl, GitHub, and archive. But recent work show that domains can be defined in much finer grained ways, capturing other aspects of variation. For instance, one paper explored splitting web documents, not just by their source, but also by their topic versus their format. And I think the fact that mixing this general procedure is kind of agnostic across whatever your data is quite powerful, which is why I think a lot of the ideas here can hopefully be used in robotics. And second, an understudied aspect of mixing and really of all these data curation strategies is the feedback loop. So from these heat maps I showed earlier, can we use our understanding of how models learn from data to actually design and collect new data? In practice, people who are training these models already obviously do a heuristic version of this. You try some data, you get a sense of, how the model is doing, and then you go out and gather some more of your good data. But turning this intuition into a more principled process could be very powerful. And that's it. So I've listed some suggested resources on general data development and mixing for LLMs. And yeah, I'll take any questions.
In the interest of time, we're going to move on to the panel discussion. Set up. Your panelists, now would be a great turn to cover the one. No sense of hearing. Divide out by still on taste. One more chair. Yeah, we did this group of chairs. Okay. Moderator. There's some microphones.
Yeah.
That's fine.
All right, so for the last part of this workshop, to conclude today, we're going to have a panel where we're going to see all the hot takes on whether data is more important, the model is more important, and what part of the data is most important in training models. I'm going to introduce our moderators here, who are fantastic organizers, Chris and Joey. Joey is a PhD student with Dorsa Sadik at Stanford University. Chris is a PhD student with Jeanette Boat at Stanford University, and they have been some of the drivers between all of the events that you've seen today. So you should thank them for all their efforts today. And then we'll have all of our panelists here today giving talks, and you've seen them before, but I'll quickly reintroduce them briefly. So from for you left to right, we have Max Simkowitz, who's a professor at CMU. Then we have Ashwin Balakrishnan, who is now a research scientist at Physical Intelligence. We have Mei Chen, who is a PhD student at Stanford University and affiliated with AI2. We have Chelsea Finn, who is a professor at Stanford University and one of the co-founders of Physical Intelligence. We have Masha Iptina, who is a research scientist at Toyota Research Institute. Ken Goldberg, who's faculty at UC Berkeley and co-founder of both Ambi and Jacobi Robotics. So with that said, I'll kick it to our moderators and hope you enjoy the panel.
All right, thanks, Rohan. In the interest of time, let's go ahead and get started. So just to kick it off, the first question, Very basic one is, and also a difficult one might be, how should we define good data? So how would you think about what makes data good or bad? And maybe I'll kick this one off to Ashwin, who we haven't heard from yet.
Sure. Yeah, it's obviously a tricky question. At the end of the day, when you decide what data to collect or what data to curate, what data to keep, it's a decision about like what capabilities you want your model to have. So your data should reflect the kind of behaviors you want your model to produce. And I think at the end of the day, one of the most consistent properties of good data that I've noticed is that, first of all, your data should reflect, those capabilities that you care about. And second, it should be the case that like, no matter how messy or chaotic your data collection process is, it should be the case that, given an input, no matter how you design your algorithm, it should be that like, the entropy of the output is like relatively, like it should be relatively clear how to generate the outputs in your data set, given your input. This doesn't mean that you necessarily have to collect like super narrow data sets. It should just be that you have designed your data sets and your learning algorithms together so that you can actually break out the multimodality of the problem effectively, so that you can prompt for the behaviors you actually care about the problem.
Yeah. No. Oh, the mic should all be on.
No.
Yes. Okay, great. I think the answer to that for me is whatever data makes your success rate go up. Now, the success rate is on is another question, right? It might be a super narrow, very specific problem with all the same initial conditions, or it might be 17 different tasks and you're looking at average success rate overall. As long as success rate is going up on whatever problem you set up that you care about, your data is good.
Yeah, I'm going to push back on that a little bit. Masha, I mean, I think it's the success rate as metric is a little bit of help out. We were talking today about speed of performance, for example, right? So there's that factor, there's the consistency of robustness, right? Because I think there's also, when you say success rate, there's a lot of questions about what is the distribution, right? And if it's robust, so variations in the distribution is in a way success rate is measured that, but it really depends on how much you're testing in that distribution. And so I agree with you in general, but I want to also talk a little bit about Ashwin, because when you say low entropy output, are you suggesting instead of being medium low?
No, so I guess it depends. It should be like medium model, like based on what you're conditioning on, right? But for example, maybe you have a data set where like there's like many ways to do a test. I think that's okay as long as like you have information about like what those different ways are. So if you like have some sort of labels like, oh, this is like one strategy I follow to do this task, this is another strategy I follow to do this task.
Yeah.
If you have that information that you can actually condition on, then having like a multimodal data set is fine. Okay. But I think you should have low multimodality but conditioned on all the inputs.
Okay. Because I was also going to say, one other question related to this is that good data, but can that data be cleaned effectively? Right? Because we have data that's easily cleaned. It might be not great data to begin with, but it has nice quality, so you can clean it. And so I'm sort of getting that, which is there are going to be these ways to fix that entry after you.
Maybe just one thought to respond. Thank you for calling me up. Success rate. I wasn't criticizing. Success rate is one possible metric that we care about. Yes, let's generalize to any metric that we care about. But you can also think about robustness as whatever task set that you design, right? So maybe you care about many different failure modes, and you design your ICs to be adversarial. And then you're thinking about either success rate or whatever metrics you care about in the context of this very robust thing.
One thing that I'll mention a little bit is I think that, I mean, generally, I completely agree that you always want the data that's going to make the model better. I think that unfortunately, like I actually mentioned in my talk, I think that measuring things like success rate for generalist models is increasingly hard, really, really hard. And so I think at the end of the day, it's like the most practical thing is going to be we have to make choices without being able to measure if those choices are impacting the right choices when we're collecting data at scale. Specifically, especially like data that's going to training these generalist models. There's a lot of really nuanced things. I mean, there's things like being able to complete the tasks like quickly, being able to have like high success rate, diversity, like lots of environments, lots of tasks, and so forth. But there's also really nuanced things like, will this data lead to the following? And if, for example, you're in a scene and the robot always does the same thing in that particular scene, then you can then condition the model in language, it might completely ignore language. And so, yeah, I think there's a lot of nuances to it. And that's also something that, like, if you tell someone who's like operating the robot, it's a researcher, and tell them like, they want that, maybe you don't want partial observability, they don't know what you're talking about. So it's actually, yeah, really, really hard, and lots of attention goes into getting the data.
Yeah, so to build up on what you were just talking about, to what degree do you feel just nuanced aspects of data quality or characteristics of the data that leads to desired behaviors can you preempt versus sort of just recognize at deployment time the model function have to work backwards from there? Are there some practices that
yeah, I think it's going to be a mix at the end of the day. I also think that maybe you like collect it is, like train on and you see what happens. You then try to correct that. No, you don't just start for it on that task, you start for it on all the tasks and kind of put together a process of it. So each thing that kind of data that you want. Yeah, and so for example, like for partial observability, you notice that like, oh, you really need to have like full quivers in the image at the start of the episode to get the robot to work. If it's really not working, if you don't do that, then you can kind of set the approach to do that.
What we found to be most effective, it's really hard to guess what exactly is going to be the right data before you start. So we have this iterative process where you'll collect some, you'll train a model, you'll watch some rollouts, you get a sense of how it's performing. That's how researchers also do it, right? But it also really works for the robot teachers. So as long as we're able to close the loop and show them what the data that they collected resulted in when you roll out the policy, that really helps them adjust. It doesn't always work, and it can take multiple tries, and maybe you go the wrong way to try to do recovery, and you have to go back, right? That's happened, but I think closing the loop has been very effective.
You're saying with the contractors?
With robot teachers.
With robot teachers. Interesting. Because I was actually curious about that. You have more personal experience in the media. I was just curious about how sophisticated are they in the sense that do they, first of all, I'm curious, there's a lot of turnover and people burn out, and those that don't, are they really getting into it and really learning how the fine nuances? Because I just don't know.
Yeah, in our case, there hasn't been too much turnover, and we're not at the same scale as Pi, so I'll let Chelsea speak to that more. But for us, it's very clear that the longer they are with us, the more proficient they become, and the more they know sort of the nuances. Oh, you have to collect in this way for this kind of task, because that would result in a just because they get it from experience and iteration.
Yeah, on the turnover part, we've been kind of quite happy with what we've been able to do there and sort of at least time. One thing I actually want to mention on like some of your previous point is that for the with regard to like measuring how good your data is, when we were working on the Detroit data set, at the beginning, and then maybe for the Detroit data set, like 8,000 trajectories, ballpark, and 500 scenes, 50 environments, really diverse camera viewpoints. When we were first trying to train on it, like a lot of policies were not working really on the data set, and we weren't sure like maybe this data set is not dense enough to be able to train good policies on it, or maybe you're like we thought that maybe there was something fundamentally wrong about the data set. It wasn't until I think maybe a year later, when CoRL trained like the Kaiser Bass model, that we actually saw a model with like a policy trained on it that zero shot did something out of the box and worked. When it did, it actually worked really well in a general studio environment. So it kind of sometimes said like it goes to show that like if your data is like a little bit too far ahead of your model development, then you might have this really painful time period where like, you just wasted like time and resources on collecting this data set. And maybe it like just didn't turn out. And so having a bit of a feedback between the data and the policy training is really helpful. At the same time, I'm really glad that we did Troy, even though that feedback loop wasn't as tight as it could be. It pushed us to like build better models that can use that diverse data.
So we've talked a lot about what makes good data so far. And one interesting thing is currently there's a lot of companies that are trying to collect robot data and sell it to other people. So a short question to everyone would be, do you think this would work? And if not, why?
Yeah, I think generally in the long term this should work. I feel like if we're not able to, consume data from like very diverse chaotic sources, then there's some problem with how we're doing algorithm development. But I do think like since the data is like so important to developing like generalist models, like having kind of like as Chelsea said, like a super tight loop between like data collection and policy learning is like very critical, I think, in these like early stages of robot foundation model development. I'll say like from I guess like my personal experience, especially when you're collecting data sets for like these robot foundation models, like it's hard to even keep track of like where the tasks in your data set. Like it's just ballooning. There's like not like really like a clear like delineation between like this one task and another. So often the way I find out what's in our data set is just by playing with them off. Which like maybe ideally in the future we have like a more coherent way to do that. But often, when trying to help find different capabilities you want, it's like very useful to like be able to immediately say like, okay, I'm going to collect data in exactly this way, so I can patch this to what I noticed and playing with it. But I think once we hit a point where we have like mature data collection strategies, which we know will lead to specific capabilities internally, then like we'll probably move to a regime where like we can more effectively ingest data from other people with strategies.
This may be vaguely tangential, but if we kind of chart the development of large language models, what we really see is that currently like most kind of valuable data is human data that labels preferences for positives and negatives. And so we've heard like a lot of really interesting comments on how to collect good positive data. But I think as soon as we develop the methodologies and models to incorporate negative data, probably like the span and kind of methodologies for collecting negative data will be not only expanded, but probably your end users will then be able to provide negative data. Like being able to get failure examples from your users probably would, like if you're envisioning what does like the robot data company look like, I would imagine some software as a service for like, like you can sell like a solar power back to like your, electric company. Maybe you can sell bad data or negative examples back to your robot company, provided you have a good Q&A algorithm to handle that.
Yeah, I agree with that. I think that we're going to care a lot more about negative data and good negative data in the future. One kind of recent anecdote is, we've been working on a benchmark for reward models, like general purpose reward models for robots. Hopefully we'll release it soon. And one of the things that we're working on is when people want a data set, this reward model benchmark, and then we're like, oh crap, like the data set like all has successes. How do we benchmark rewards if we don't have failures? We haven't done all the safety research. What we did is we took hindsight, for people who know hindsight experience replay, we actually did the opposite. So we turned successes into failures rather than turning failures into successes to generate labels to augment the data. And yeah, we agree that more negative results.
Or also useful for role modeling and things like that, right? I think ultimately you have some way to post label or curate your data. All data will be useful in some way. Yeah. No, I was just gonna say that having a talk today was about failure detection, right? So that you think of all the different applications and if we can detect these failures, then we can do recovery, we can think about curation, we can think about how we mitigate these failures, right? All these different things and world models, right? Will unlock so many different things. I think it's great that these companies are collecting all this data, even though it's not all high quality, as long as they're doing it ethically as well.
Okay, so let me also try to be a little contentious and suggest, do we all agree that it should be diverse? And when I'm thinking of in particular, this week we've seen these great demos of laundry folding, towel folding, right? Out of Dyna, where they're just folding one towel. over and over again. And then Generalist just released a demo of this Lego assembly. And I don't know which way this general model. They sort of put in this, but it seems like it's been very friendly to on this Lego task. It was an impressive task, very impressive. So I'm just wondering how do the other panelists feel about diversity versus sort of top down, starting very generalist, and then training generalist models versus this approach that some are taking, which was bottom up, training very specialized models first. Now everybody hates me.
Well, so I think that companies like Gaia and Reynolds are using kind of a very general purpose pre-training models and then figuring out how to adapt them. I think both the diverse pre-training and specialized fine tuning are really important and valuable problems. And the specialized fine tuning is the thing that will, at least in the short term, probably be quite important for actually getting these robots in the real world. So I think it's like figuring out both parts of that puzzle seem really important to me. And the diversity of data is like, I think they're really critical for that first part. And I think we omit, I guess one thing that we found in Pfizer is if you omit the pre-training, like a lot of your doesn't work. Because you need the pre-training to help it understand what to do in like various cases. But if the chart is like configured in a weird way that you didn't see in the post-training is that pre-training helps back it up. And that's one of the reasons why I think like diverse strategies and pre-training is good, is to get more exposure to diverse states. So yeah, I think both are.
Well, so you've talked a lot about various aspects of data that you might want to target in the collection phase. Talked about how different types of learning objectives between prediction learning and role modeling, they benefit from different kinds of data. But we're talking a lot about us as building human teams, to collect data for us. In 5 years down the line, or let's say by 2030, are we still gonna be collecting our own data, or should the strategy be to accelerate as fast as possible to the point that we can be deploying models and having robots collect data for us, kick off data flywheels and things like this? Well, I think unlike in say like applications like AEs, for example, where it's like a super safety critical application. I think robotics actually we can get to like calling about flywheels without like having like near perfect performance for some tasks. Right? So I do think like right now maybe a lot of like the generalist robotic work is like kind of at this point of like, what is the strategy we can take so that we can get over that hill, so that like people will want to start putting this into a flywheel. And then once we get there, we can improve pretty quickly. And I do believe that like, doing large scale robot data collect is like one of the best ways to kind of get over that bump initially. And then once you have like, flywheels going for a bunch of diverse tasks, then I think you can like really get into the flow of the amount of data you get, and as a result, the capabilities.
Robots should do more work.
Oh, sorry.
Maybe a small thing to add as well, is that when services for some of these robots become products, we're going to start demanding success rates that are far above probably some of the things that we're seeing in our current models. And it will end up being actually unavoidable for the robots. We'll have to collect data on those tasks, because otherwise we won't be able to see the tails of the failure distribution without having some of that. And I imagine also algorithmic things will change as well. Like hopefully once pre-training is good enough, we can actually get reinforcement learning to work in a very reasonable way. We can still explore from very good priors. We'll be able to use DLAs for good task decomposition. And so I sort of imagine that it's not even going to become something that's sort of more effective. It's going to become something that's a necessity.
I think there's probably two parallel threads there. One is construct a deployment site where we know that we're safe and there's probably no humans around it, in close proximity, or they're safe from whatever the robot can do. And I think that's a good idea. I think that will bring progress, and we should do it. But simultaneously, we really need to be thinking about how to get to the point where we would feel comfortable getting these workplace systems in environments where I think that's the ultimate thing that a lot of us would like. In there, we still need to do a lot of research to learn to live in our area. This is like way on the autonomous driving. Where we really have to make sure that we remain safety critical and we really figure out those safety pieces.
So I'm not safety now. I'm curious how others feel about this in terms of my sense is we should do whatever is needed to get to that reliability, which is often a mix of the old fashioned engineering with models. And I'm just curious how others feel about that. Are you opposed to this in principle? No. You're not opposed? You are. Oh, I'm opposed. Okay. Justin. Afterwards opposed. I'm just curious. No, just I'm just curious to see that more because sometimes it's not either or. You know, you get up to speed, and then once you collect the data, then you can gradually, pare back those other modules so it becomes end-to-end efficient.
No, and also, I think that perspective of do we want to see to get to the flywheel kind of like helps keep us honest about when our like aesthetic preferences are taking over. Right? So my personal background is actually from the theory of reinforcement learning, where we like sort of imagine, a baby in the world that's drawn and it doesn't know what to do, and that's a fake product. And I think you have to come to terms with sort of like what are actual problems. And I think that by good engineering, you sort of put yourself in a regime where you're actually tackling what's relevant, rather than just kind of creating like academic fictions for the purpose of introspection. I mean, so it still can be valuable, but yeah, you should put yourself in a regime where you look.
On that note, I think that it would be interesting to toss the conversation over to May. So May just gave a great tutorial on data mixing for LLMs. And so one question I would have for May is like, what should we take from LLMs into robotics? And for the robotics people, what should we ignore from LLMs?
Really good question. So I think in terms of things we can take, so pre-training data sets for language models are absolutely massive. And so a lot of times, people just try data selection technique on like one subset of the data, and they're like, oh, this worked, we'll just keep on using that thing. But there's actually so much noise in pre-training data that you really want to account for the effects of just like randomness and think about the robustness across even just like, you pick 1,000, like a billion random tokens with this seed and another seed, and seeing if these like data selection methods or data mixing methods are actually consistent across noise, because there's just so much variation if you're looking at a web data set. So I think that's one thing that's really struck me in the language model space. I think things to ignore. I don't know if it's really something to ignore, but I think there's like something about the construction of language that's very broad and there's a lot of facts. So a lot of things can kind of be just memorized, where it's like you just train on the fact and then the model will know the fact. And I think that allows for a lot of data selection and data curation principles to be almost like cosmetic in a way. So the example I have is like all of these rewriting methods are like, you rewrite this sample to the style with Wikipedia and it gets better. And so I think a lot of these language model data curation techniques kind of rely on our human intuition of what looks like the data. Be like, well, this looks cleaner, this has the structure. And I think that's because language is just so broad that it's easy to kind of do this matching. But I think maybe for robotics, there's kind of this I think you care about how the robot does the thing and not just like success sometimes. And so thinking about like, do you want to create data based on these more like human intuitive, like this looks like good data or not? That makes sense.
That's a good question. Do you think there's a big difference in history, like robot data currently is higher quality in Common Crawl, like where the people collect it, and Common Crawl is like anything anyone says, so do you think that's changes how we think about things?
Yeah, I think definitely that changes things, like the fact that language data is so noisy requires you to really like focus on consistency and robustness of these methods. So like, if you try this method on like two different settings that like slightly adjust the objective, and it's like working well in both of these settings, you kind of know that it's would run that noise. But I think if your data set is cleaner, maybe you have to worry about these things less. But I'm just thinking like as you scale up and get more data, maybe some of these issues will arise. You can't start keeping track of all the quality of everything.
With regard to the memorization and like all the factual knowledge, it's like inside these LLMs, it kind of makes me wonder if like robot foundation models will need to keep quite as smart as a result, because they don't need to memorize, like, presumably they don't need to memorize so much like actual knowledge. Because usually, you don't need to know, I don't know, like Shakespeare's birthday or something to like pull the title. Yeah.
Is there anything else we should ignore from language models besides the model size? Continuous actions versus discrete, a big problem. No, we should take all of the lessons from language models and just do it again.
One thing is that a lot of the developer takes to just to be that you can like verify everything immediately, and that's like not true in any real world domains, like a lot of language model domains, and so that's gonna be a hurdle that like where we can't just like copy exactly what the domain. Yeah, but I do also think that there's a lot
I think maybe two very positive things. One is the safety information knowledge, especially as we know tomorrow with robots and that consequences to the robot as the environment around it very, very quickly, which it could also have consequences and it's becoming more of an important thing, they're more delayed. And the second one is I don't personally think that we'll be able to get to the scale of data that language has in the world, just based on the demand and how much there is. So we're gonna have to be a little more creative in some ways with how we use the limited data that's available to us, whether that's for curation or mostly priors or biases.
You know, one thing is, chain of thought ideas and things like that, people are adopting that for robotics. But we asked a little bit of variation on that, which is what about how can you for this field that robot data can help, not even LLMs, but DLMs improve? We've been doing some experiments with extracting data from actual Droid. We used a lot of that to generate EQAs and sort of a benchmark, but also for the training of those goods. There seems to be a feedback loop that you train the VLM on its robot data, then the VLM gets better at evaluating and cleaning with robot data. So I'm just curious how others feel about that sort of hybrid.
I'm hopeful. I think that we need the data to be diverse, and I think it's very important diverse data that can take better loves. I think long term, hopefully improves the elements too. I think there's a lot about like either just vanilla models that don't like really fully understand the world we live in, because it's all through this mirror of human text, or through this perspective of human text. So yeah, a lot of it embodied data. It needs to be diverse enough, it needs to be large enough, because the robots so we can have them be collecting the data, getting the experience in the world, and I'm so like, but it's not diverse enough. I don't think it will quite reflect it.
I guess going back to Joey's initial question, I think one other maybe obvious thing that's like pretty different between like LLMs and robotics is that like for LLMs, like the pre-trained data set already largely exists, right? Internet, robotics is collecting that for the first time. I think that comes with both challenges and opportunities, right? Obviously, ideally we would have this whole robot data set already. But now that we get to make all the decisions on how to collect it, I think like there's a lot of interesting questions on like what is the right composition of a pre-trained data set so that you can like quickly fine tune later or list the behaviors you want. Like I think maybe on the LLM side, we have to think about the questions in the exact same way because we have a lot of the data already, and maybe we'll do a lot of data like later more for like post-training and getting like really good performance. Probably have time for one more question here. So we're talking a lot about the relative size of the training data sets, models, robotics. There seems to be some convergence on the idea of like data flywheel being important, but that being contingent on a certain base capabilities of the model. You know, Josh, when you said that collecting the human files is probably the best way we know how to do that right now. So on that premise, you could dedicate all robotics researchers to, let's say, a year's worth of data collection to create that pre-training data, rather than all the research they would produce when you do it this enough. Interesting. I mean, I don't know. Actually, I don't know. Robotics researchers are like the best at necessarily going to data. But yeah, I mean, I think it'd be great if we have like a large number of people who like collecting data. I think like long term too. I mean, maybe this is kind of like a pie in the sky notion, but like it would be nice if there were like economic incentives as well for like people to end up like collecting robot data that we like. So, you know, these aren't concrete ideas, but like, you know, maybe if there was like, you know, a game that everyone really like playing, where like, you know, in the process of playing that game, you're gonna collecting a lot of data, or something that would like get people incentivized and excited about collecting robot data that we can just use for the research community. That feels like something that would be a really cool way to spend time.
Yeah, I completely agree. I was gonna say, gamify the data collection, but to answer your question, no, I think the robotics community is too small and it will actually be different.
So I would say that was like sort of, in some ways, the word initial ideas was right. It's like, it's 30 years of data collection, and we're originally scheduled within the lab. But then we asked the people like what they want for data, and they want to be committed, and everyone said yes. I'm like, okay. The people like to contribute to stuff, which I think is great about our community. I mean, I think that now that we have ways to have other resources for stocking data, the answer we know. But I think that if we didn't have those kinds of resources for stocking data, then my answer would be yes. I do think that like despite maybe limited collaboration capabilities, I think that researchers have a lot of intuition for like how to set up the scene in a way that leads to data that's really good for the model. So researchers and input actually much with excellent data.
You know, speaking of gamification, I mean, in some ways, Chelsea, I remember when you said the objective, if you put in 40 hours of data, it would be a cloth of paper. Right? That worked for a lot of my students. It was really effective. And it was a kind of gamification, and it worked. It was really clever. I think that is interesting. I'm not sure I like it. And especially if it's a fun game like Pokemon or something like that, right? You should really go out and get a huge number of people. I was also thinking something like a Peace Corps. So, because I think it's actually helpful for all of us to do it, mostly because we can learn a lot from what it's like. I mean, it can be incredibly tedious, and I think to know how that is, and then think about how to help the contractors and guide them and supervise with them and then maybe design that next generation of interfaces that makes it more palatable.
To that point, a lot of the past papers that I've published in the last year or two have been inspired by sitting there and watching other Black teachers work and seeing their pain points and what works and what doesn't. Right? Data curation is a way to help them get to a place where the policies better, even though they don't need to figure out the exact mighty things that they need to stop doing or not turning on. So it is very powerful, and I do recommend that people watch data collection or do it themselves.
I have two hot takes. You guys want hot takes? Yeah. So I think all these we start thinking about specifically like I've noticed being really helpful for me coming from outside the field is like seeing like the weird minutia and details and idiosyncrasies of things that you can only really get by being around Harvard, being around data collection. But maybe my two hot takes are first, even if it's the thing that can move robot learning as a field the most forward, we still also need to preserve kind of like certain cultural norms of academia so that like students also have practice like going around and wandering in the wilderness and like not really knowing what they're going to figure out or like asking questions where they get a little bit lost. because inevitably you'll run into challenges that our current paradigm doesn't hit. And if students aren't both given like experience of what is working and sort of direction, but also like experience trying things out that are somewhat kind of off the beaten path, I think we'll find stumbling blocks later. And I think the second hot take is if we have a lot of people, we gamify making data, then there needs to be like some sort of social dividend that like repays that to people. Because inevitably that data that we'll collect, a few people or actors will be able to take advantage of it and like do really, really well. And you know, we're not set up as a society or as an economy, or at least in the US, we're not, I don't know how, hopefully things are better here, but we're not set up in the United States to kind of allow people to like really reap the benefit of the economic sort of utility that they're generating by collecting these data. And I don't really know how we solve that problem.
Anyone else? No one wants to vote for the data. All right. With that, I think we have time maybe for one audience question, and then we'll wrap up the panel. Does anyone have a question? No. That's also okay. I guess we can end with another very, very quick question, which would be, in 5 years from now, do you guys still think that we will be trying to collect large data sets for imitation learning? Or do you think we will just be doing something entirely differently? And why might that happen? Will it be because imitation learning will work in 5 years? Or will it be that like there's some other breakthrough that leads to a totally different direction for the field? Maybe that's too hard of a rapid fire question. That's an answer to the question. It's good.
RL plus like targeted task specific data collection, like to warm start the RL.
All right, I guess we have one or two predictions.
I'll say, I think that we're waiting for a breakthrough in simulation, which could pop in at some moment, and that would change things dramatically. Or let's say video analysis, right? 3D video analysis is breakthrough could happen there. So people are working on both those fronts, and if those happen, that would change.
This is a big opposite of what I say, but I do think it is really valuable for different parts of the community to work on different problems, and not everyone to be kind of going to a single approach and that sort of thing. So I guess that there will also be kind of a diversity of approaches in 5 years. And there's one that I'm betting on, but I also think that other people will be betting on all sorts of other things.
Can I ask about that? I mean, I go back to your quote, which I loved earlier, don't be a purist. And it does feel like a lot of the talks where it's imitation learning or it's reinforcement or maybe chain of thought is even so. Do you guys see hybridization of this, or is it crazy out there?
RL only works with pre-training.
RL is with imitation. The imitation and then RL. Imitation is. But at least that's my take. And other ways that I realize that people like using simulation with this, or using a control theory, or using your models, or all sorts of things.
All right, I think it's time to wrap up the panel, but if you guys have other questions about other things, like maybe feel free to find them at some point, but I'm sure they also all have many things they need to go do. So let's go thank the panelists, and then we'll get on to the world. All right, yeah, thanks so much. Thank you, sir. Thanks so much. Thanks, man.
Where did you saw? Yeah.
I sent it to you Slack. Here. Just. Basic full screen.
Dude, nobody cares.
Yeah, no one cares.
Oh my gosh, it's fine.
All right, thanks to Rebecca for presenting one more, and it's again at the very end.
We do have one best paper award today. So, yeah, with that, we had 4 nominations. Yeah, so the 4 spotlight talks were all nominated for the best paper award. After some long and difficult deliberation, we have given Data Mill the best paper award. So if you're from Data Mill, please come find us later. We'll email you a certificate and some other information. But yes, thank you all for attending. Cool. That's it. Cool.
That was fun.
That's good. That's all.
That's good. That's good.
I tried to be spicy.